to Friday, which is the official launch of the Climate Crisis AI Hackathon. Yes, I will definitely move back so that I don't have you can't see my nose hairs.
You look great, Tim. And it's great because you guys can get to see your beautiful smiles, unlike earlier this week. So before we begin, let's introduce ourselves for those who are wondering, who are those two amazing, good-looking people talking to you now? So I'm Monika Potocki, and I'm co-founder of MTL Green, partnering on this event with AI Launch Lab and with my co-host, Tim. I'll let him introduce himself.
Yeah, thanks so much, Monika. So Timothy Pereira, co-founder AI Launch Lab. Been working on organizing hackathons and AI R&D mentorship programs for the last close to 3 years. Before that, my background is finance, but I don't want to get too much into that since their time is not much time for us to get into everything. So what else on the agenda do we want to talk about, Monika?
Yes. So actually, Tim, let's give a bit of context to people. How come now today we're not in the studio and that people are seeing us with this great banner behind us, and what happened since last time we spoke to our audience?
Yeah, it's a really great point. So on Monday and Tuesday, if you had been tuning in, you would have seen us in a studio, and we really wanted to try to have some sort of a high fidelity, high production value live stream going on during this event, and definitely it didn't turn out the way that we wanted it to, and I will definitely apologize to everyone who was watching on Monday and Tuesday. The sound quality wasn't what we wanted. There were many technical issues. So this time we wanted to do something that we knew we could deliver on. It's a little bit less with less flair, but I think it's stable. And for the French translation, for anyone who's on the Zoom call, you can see in the bottom of your screen towards the right, there should be a button that says interpretation with a little icon that shows like an earth in a sense. And if you click on that, you can listen to the French feed. So definitely encourage you to do that. We have Julie, who is our fabulous translator or interpreter for this event, this part, at least the first half of the event. So thank you, Julie. And yeah, so basically that's the reason why we're here. The other reason is that, since we're in Montreal, in Quebec, where there's a lockdown happening right now, and this event goes beyond 8 p.m. Eastern Standard Time when the lockdown goes into effect, we also need it to be at home.
Yeah, good point, Tim. But the good news about this is that this weekend will be awesome. And we'll make sure that all of you are learning and having fun, and that this virtual experience becomes one where you will really feel that it's meaningful and that you can connect with others. So our team has really innovated on that front. Hopefully you'll enjoy the tools and the format of this hackathon and have fun and learn throughout it all. So actually on that note, let's talk a little bit about the tools and how will you be connecting this weekend for the hackathon. So as you all have received an email last night, essentially there are two main tools that will be used across the weekend. The first one is Miro. If you haven't yet joined or looked at Miro tool, I strongly suggest for you to go in already and watch. Also on the AI Launch Lab YouTube page, there's a special video, 40-minute video that our colleague Jason has created that explains how this virtual world has been designed to allow you to collaborate and get the key resources in this space. So really go on Miro. It will be the place where you'll find information on any type of workshops, information on the challenges, connecting with mentors. But most importantly, you'll have a space for your team, once you team up, to really create and apply some key concepts within your design and your project. So you'll have a working space where multiple users can play in it and make it your own. So we're really looking forward to seeing what you guys create on that Miro board. Also, to communicate, we have created a few Slack channels. So Slack might be a tool most of you are more familiar with than Miro, but on Slack, you'll have the opportunity to also ask questions based on every type of challenges. So we have 9 distinct challenges where you can ask questions. We also have as well an announcement channel that on Miro you can find so as well. And there's a few help channels that you can refer to if you need any information or extra help. Also for teaming up, I know many of you are so eager to start, and we are eager for you to team up and start working on one of the 9 challenges. So what we're suggesting to all the participants is to team up. What we will be doing is providing you under the channel Team Up. So go in the Slack channel Team Up, and in there you will find a link to a platform called Rally. And on Rally, it's essentially a video and voice communication partner where you will find different rooms based on the 9 challenges. So if you know that you're interested in a specific channel, there'll be various rooms set up over there. And once you enter a room, you'll have the opportunity to split up in different tables and find out who you can pick as your team members. So there will be facilitators and team members in that link throughout the day, today and tonight, past 8 p.m., where we invite all of you to join and team up if you haven't selected or come forward with a team already. So don't worry, all the information will be there, and we'll make sure that you find a team, and we'll explain the process a bit later at the end of today as well. So actually on that note, maybe Tim, you can tell us, what are we expecting this weekend? Like, do we have what types of people, resources, support will we have?
Yeah, this is one of the exciting things about this weekend. We have really the entire organizing team and MTL Green as partners have managed to bring in a ton of mentors for this weekend, as well as a lot of facilitators as well. So there should be quite a lot of support for everyone who is, hacking within their teams. I think we have something like 30 mentors that are going to be available this weekend. So really exciting, and we're so honored that they would choose to spend their time on their weekend with us during this hackathon. The facilitators as well are really here to help and support you in any way that you might need it. To guide you and to point you in the direction that you might need to go on your journey. And also just a little bit about today as well. We had the workshops and talks on Monday and Tuesday, and some of those are going up or have gone up already on the AI Launch Lab YouTube channel. And we're gonna. I think also we do have Tuesday's entire live stream up there, so you can watch that as well. Monday, we'll try to get some of them up over the weekend as we can. Just needs to be some editing done on those. But for today, we're going to have some amazing presentations about the challenges. So that's going to be between 2:30 and 5. So all of the 9 challenges will be presented, and you can ask your questions during that time. Then there's going to be a break, and at 5:30, we're going to start with the keynote talks. So these are going to be some of the most awesome experts that are going to talk about climate science as well as AI and how AI can be utilized to address the climate crisis. So we have starting with Alain Bourque, then we have David Rolnick, we have Priya Danti, and then we have Sasha Lucioni. So a really exciting lineup to add to all of the awesome people who are going to be presenting the challenges. So definitely look out for that. And then after that, we're going to have networking for attendees. So basically this will be with the rally rooms as well. So it's a really fun experience if you haven't tried it before. You basically have this kind of a setting that feels like you're in a restaurant or a bar. You can hear kind of the background noise of the other tables that are around you. You can choose which table you want to go to, and you can swap. And I'm not sure if we're going to randomly, I think probably we're going to randomly switch you around, but I'm not sure if that's what we're going to do. But anyway, it's going to be really fun. And then also for participants, it's going to be in Rally as well, where we're going to have tables for each challenge type. Is that correct, Monika? I believe so. Yeah, and so
that's it.
So you'll be able to go in there and speak to people who are interested in a similar challenge type. And we're going to really try to facilitate the process of forming teams during that time. So that's the schedule. And unless I forgot anything, Monika, I think that's what we have to look forward to today. But then also Saturday, there's going to be lots of things going on for participants, including yoga, including some fun team-to-team, optional for people who want to partake in that. But there will be some I guess I was going to say bonuses. There will be some benefits to partaking in those types of activities, which we can discuss later. I think there's a checkpoint system. So this is basically to try to encourage collaboration and to encourage people to really get the most out of your weekend. And then Sunday at 6 p.m. Eastern Standard Time is when submissions are due. And then we'll have some closing talks from some great speakers. And I'm happy to announce that we have Nicole, and I'm not sure if there's another speaker as well from the Academy of Sustainable Innovation. And also we're lucky to have Sylvain Carl from Second Muse and as well from Real Ventures. And we'll try to show a couple of the videos from teams as well to really, show people what was worked on and what amazing things were achieved this weekend.
Yeah, those are great insights, Tim. Thanks for that. And I want to re-emphasize, so tonight's agenda is really from 2:30, so in less than 15 minutes, we'll have presenters present till 5 o'clock, each of the 9 challenges. So now on the screen, I want to pinpoint everyone to look here and remind everybody that we have 5 challenge types. Okay, so here we pay attention to the color codes and the names. The 9 challenges have been categorized under a type of challenge. So we have Kaggle, that's really bringing about a better model that what is existing. I think this is our most popular one, actually, that people are interested in this weekend. We also have data visualization. So it's really how to explain and use this analysis to communicate data insights. We have AI artists, which is a one-of-a-kind type of challenge where we use art to provoke insightful inspiration for those that observe the information, the data, and can extract some key elements from there. We have also the open challenge, which is where you'll bring about your own challenge and you get creative. So it's a bit of an open pitch style, and you can use whatever format or approach that you want with the type of challenge. And last but not least, projected impact is really how can you analyze the impacts on human and environment by using data to project the impacts on climate change. So it's a more specific one. Also on the right side, you guys will see climate approach. So since this hackathon is about how can AI be used to tackle the climate crisis, it's really important to understand the 3 types of climate approaches. So adaptation, a quick reminder, it's the type of challenge that we try to see how can we adapt to the climate that is changing. Mitigation challenges are those that rethink, retransform a certain system that will really bring us to a net zero outcome and bring a new sustainable model to an existing format that we do things. And finally, awareness is really about how can we perceive our actions, track our decisions, and making us aware of how our impacts lead to the outcomes that they bring. So based on that, maybe we could look briefly the challenges that we'll be presenting in just 10 minutes from now. There are 9 challenges. And out of those 9 challenges, okay, maybe do we have the slide here? If not, I can show it very quickly to you guys. All right, just a moment. Perfect. So as you all know, there are 9 challenges that will be presented to you. And here we can see the order of those 9. So we have amazing designers of each of these challenges. So you'll get access to data, information, insights, and they really tackle true problems that impact climate change. So we'll be starting obviously with the Be Healthy, followed by Challenge Wind Energy, then AI Art, followed by Reducing CO2, then Sea Ice, Sewage Overflow, Smart Building, Super Resolution, and Remote Communities. So you will be seeing this graph on both the Miro and Slack channels, but also in the feed that we presented on Tuesday on the YouTube channel, where you can really see each of those challenges under which category do they fall into in terms of the approach, but also which climate approach do they mainly approach and that they are concerned about. So use this as your guide. It will also be the breakdown of those challenges. You'll get more details. And once again, the language is really the hashtag challenge and the 2 keywords. You'll find this language on Miro, and you'll have a specific board for each of them, but also in the Slack channels. So use that as your reference point also when you will be submitting your challenge and dev post. So that will be the reference for each of the 9 challenges.
Awesome.
So I think we still have a few more minutes, so maybe we can cover a few other things, such as maybe thanking the people that were involved in this hackathon.
Yeah, absolutely. It's we definitely could not have done this hackathon without all of the partners that you see above me here and behind me. If you can see some of them have helped in many ways in terms of being a challenge mandator. Some have provided money. Definitely want to give some big thanks to those who sponsored the event, because definitely there's costs associated as well. So that would include CFAR. They were very, very generous with us in terms of supporting the hackathon. And also the Concordia Student Union was a very generous sponsor. Concordia Council on Student Life really helped to make this happen with funding. And also Dawson College were very generous with us for this event. And I noticed I'm getting blurry. I don't know what to do about that, but hopefully we can get it fixed. Anyway, so definitely thanks to them. And we should get into maybe judging criteria for a bit, or is that a good time to talk about it, Monika?
Yeah, sure. Let's mention it. So all the challenges will have a panel of judges. You will find their biography in Miro in the main stage, where basically you will see our 10 judges that are experts in either AI or the climate data. From there, the judging criteria are exposed to you. So if you go in the Miro board in the main stage, on the presentations, you will see the judging criteria there. But since we have Ming with us, I'll let Ming say just 1 or 2 words on how those criteria are done for judging.
Awesome, amen.
Hi guys. So give me a second. So I'll be talking a little bit about.
Oh, I think you're mute, man.
Yeah, I mean, just
can you guys hear
and
me
you
now?
have 2 minutes for this segment.
Okay, so pretty much we have 3 general criteria for all the challenges. There'll be model creativity, and functionality. So those criteria are going to be for all the challenges. We're going to look at how well your model is sufficient in addressing the challenges, how creative you guys looked at the solution, and how functional your project is. And then we also have challenge specific criteria. So for Kaggle, we're going to look at accuracy, data visualization, we're going to look at your design. For the AI artist challenge, we're also going to look at your design. And for the open free pitch, we're going to judge you on your presentation if you clearly convey the information. And for projected impact, we're going to look at relevance. And you guys will also be judged on how well you guys implemented the climate changes approach to your projects. So the three big ones that Monika mentioned were mitigation, adaptation, and awareness. And lastly, we're gonna look at how well you guys collaborated with your team throughout the event. So we're gonna look at teamwork, your engagement, as well as how well you guys use the artifacts like the boards, and how much you guys participated with your team members. And that's all I have for you guys today.
That's
Awesome,
great.
thanks, Min, and also even not just within your team, but with other teams, right? We really want to foster kind of a collaboration amongst everyone in the hackathon, and it'll definitely be seen as a positive with regard to judging if you're helping other teams and collaborating rather than just working in a silo.
Absolutely. And that's where the Miro board will be our reference point with your level of artifacts, collaboration, participation. So definitely use the team space in the Miro board that you'll be working in, and also the facilitators that will be there to keep you guys happy, answer questions. They'll also be there to make sure like your participation and your understanding is always on point. So thank you, Min, for that.
So we only have a couple more minutes before we start with the presentations, Monika. That's very exciting.
I know, two minutes, and we'll go each one 15 minutes each. Each speaker will be talking about the 9 challenges. And from there will be a Q&A also segment within each 15 minutes. So during the live stream, ask your questions. We'll have a facilitator ask them to the main challenge presenter. So feel free to do so. This is your time to ask questions live before we start teaming up and working hard later at 8 p.m. tonight. Also, I want to pinpoint that we'll have also something called ice freezers. So we love icebreakers, but we don't like the ice breaking, as you guys can see with the climate crisis and the ice sheets melting. So this will essentially be little breaks and games where you'll get to interact, meet other people, but also take a mental break from the heavy workload you guys will be working on. So stay tuned with our schedule today, Saturday and Sunday, because the deadline of submission is at 6 p.m. Eastern time on Sunday. So once we're done with tonight's presentations and our keynote speakers, that's when you guys start to roll and go crazy. So without further ado, I guess we can introduce our first challenge presenter, which would be Chris Adams from Dawson. And essentially, Chris Adams is part of the sustainability office at Dawson, and he will be giving more details on the challenge called Be Healthy. Okay, so you guys will see here on the screen the reference of Be Healthy, which is really an amazing challenge. It's a projected impact data viz, so one or the other, but it tackles mainly adaptation. So without further ado, and we're perfect on time, I'll let Chris Adams present this challenge.
Thank you. Can you hear me and see me?
Do we see Chris?
Yes, we can hear and see you.
Okay, thank you. Thank you for that welcome. Very quickly, in the 10 minutes I'd like to present and then leave it open to questions. My background originally was wildlife and fish management, and then I went into education, particularly how to use nature to teach any topic and reconnect people, community, and nature. And I'd like to begin with the little platter I have beside me. And we are going to be talking about, as the title suggests, bee healthy, and that's BEE, the honeybee, and how important they are and what impact climate change is having on these important insects. So, for example, if I just take this snow pea that I will make for supper tonight, it probably grew for about 55 to 60 days to get to this stage, but it was a flower for under a week, and that flower had to be visited by a bee to pollinate it so it could make this fruit that we eat. The same thing with an apple or a pear that I have here. So when we have an apple in our hand, it might take me several minutes to eat this, but it took 150 days to mature. And it was a flower on an apple tree for 3 to 10 days only. And if that flower is not pollinated by the honeybee visits it, takes pollen from the flower and puts it into another flower, and that pollen is the male part, and then it goes into the female part to make the seed or the fruit. Our food production is really influenced by when the flower comes out and whether or not the weather is good for bees to pollinate them. So in fact, apples are a multi-million-dollar industry in Canada, certainly in Quebec as well, and they are almost entirely dependent on the honeybee for pollination during that 3 to 10 day period. Strawberries would be before that you see in back of me, blackberries as well, blueberries, peppers. So that sets the context for the importance of what I'm hoping people, the participants, can do for us. Is there a way we can look at climate data, weather data, more specifically on a daily level, and has it changed to better create conditions for the honeybee, so they're actually going to be pollinating more, creating more food for us, creating more honey, which they also make by taking basically nectar, water with sugars in it, that they evaporate that water to make the honey that they need for the winter. They make enough that we actually take quite a bit from them, and we eat that. So it's quite concerning. And in a moment, I'll have a presentation, a slide presentation. I'll show you some of the variables. They need a certain temperature to fly in, generally above 10 degrees. They don't like windy days above 25 kilometers per hour with these wind conditions. Are there more storms now, perhaps? Are there more rainy day events that would impact bee activity? And then specifically in the spring, where we need those flowers pollinated by honeybees. So climate change and this one creature, this one insect, the bee, really ties into our food production in many ways. And then we talk about the economy, jobs. We talk about, of course, food security and the amount of that food that is produced. So I'm going to switch to screen share, and I'll just have a very basic presentation. And I'm hoping, can you see the full screen now?
Yes.
Okay, so I'm going to give you a context of an issue that we'd like people to work on and perhaps create a predictive model, maybe make a visualization of what bees are doing. In this case, I'll drill down to Montreal itself. So this is Dawson College, the college that I represent. It's the largest college in the city of Montreal. And we're just several kilometers from downtown Montreal. So we call ourselves an urban college. And on our rooftops, we have honeybees. And on the left, you'll see a box hive. There could be as many as 50, 60,000 individual bees. The center photo shows the queen right in the middle. She has the long abdomen. I'll try to get my cursor on her. Here we go, right there. And these are all the worker bees that are female. Only the female bees do the work. They're the ones protecting the hive, taking care of the young larvae in the cells, collecting pollen outside and creating the honey. The only function of a male is to reproduce. And this female is laying up to 2,000 eggs per day. And on the right, you see, we're checking on the hive. You see the bees on the frame. And this is where the young are actually, the brood, we call it, are produced, and honey is made as well. So weather is what dictates whether the bees will be active or not. And we're very curious to see what climate change is going to do to these bees. I should mention, perhaps I'll just go back, when you see that hive with a bit of snow on it on the left, the bees keep that hive at over 30 degrees Celsius all winter. So they're in there moving, they have this massive ball, they're moving in and out, they're keeping the queen very warm. And even the number of days that go above the freezing in the wintertime are important, because then the bee comes out, and if there's a sudden freeze, they lose that, and they could die, and they're losing valuable heat. So we don't want them to come out of that hive in the winter too much. So another question would be, are there actually more days above zero than perhaps we had 20 years ago? And that would be really important for us to know as well. This gives you an idea of where Dawson is on the island of Montreal, and the bees will travel about 4 to 5 kilometers at a max to any flowers to collect pollen for their young and to take the nectar that they're bringing back to make honey. Although most of their activity is within 2 to 3 kilometers. So even though Dawson only has 2 hives, let's just say for the sake of argument, we have 100,000 individual bees. You can imagine how those bees are traveling on every sunny day, pollinating flowers and gardens, including our own vegetables on our rooftop, and that are really important to have there. And then conversely, if you have a lot of rain, if we have springs that have more wind events and more storm events, the bees are in their hive and they're not pollinating. And if you happen to have a lot of rainy weather during those 3 to 10 days where the apples are blooming, that's really serious for anyone who has a backyard apple tree, to the farmer, of course, that may have thousands. So farmers actually take truckloads of bees and put them into orchards so they can pollinate very quickly. So what we are really interested in is knowing at the top here, there's a lot of writing, but I'm going to go through this as quickly as I can. Knowing that the bees do not like windy conditions. They don't like extended heat waves where it's 34, 35 degrees. They don't like to go out in the rain. They're less active on cloudy days and temperatures below 10 degrees. They like sunny days, what we call days with a lot of solar radiation. Would there be a way to mine Environment Canada weather data, which we have? You can go back almost 100 years and you can look at soil temperature and wind events, all of the things I've just mentioned. And can a predictive model be made that in fact something is happening in the spring, something's happening in the summer, that we have either better conditions or worse conditions for honeybees? That would be really interesting to know. As well, I mentioned any degrees that are over, could be over 5, could be over 10 degrees. We'll have some bee experts to help us out. Are we getting actually more days that are warm in the winter that might affect the strength of the colony itself? We'll also have many years of data of honey production in different hives correlated to the weather, so that in fact you can also make a correlation between the type of weather and how much honey is produced, and are there any trends that can be identified based on mining some weather data. So that would be one, this predictive model using weather and honey production. And then the other one is a visualization of types. If it is possible, I put some statistics here. For example, just 1 teaspoon of honey that you might put into tea or might just have on a breakfast, that represents 12 female bees in their lifetime, visiting about 30,000 flowers and traveling approximately 1,250 kilometers when the conditions are right. So you can imagine going through even a small jar of honey and the incredible amount of work that's involved, the kilometers traveled. I mean, even a small jar of honey would represent hundreds of thousands of kilometers. And I was thinking, is there a way to take some of this data and make a visualization of what a bee is going through in an urban area like Montreal, dodging traffic, buildings, looking for flowers to create the honey that they do. And we do have only 2 hives, and we produce kilos and kilos of honey that we give to our staff. Again, very dependent though on the weather conditions. So I'll just go off screen again, just give me a moment. So really, again, 2 things we're looking for: some type of a predictive model looking at honey production or mining the weather data and what is happening, and can you create some type of a prediction as to what will happen to bee activity? Will there be more days for bee activity, which would be great news, or would there be less depending on how the weather is actually changing? And then again, the visualization. So that is the presentation I wanted to give. I realize that's very quick, very important topic, and I'm certainly open to give any more information that is asked or answer some questions.
Hi, Chris.
Hi.
I hope you can hear me okay. I'm just from our chat here. They're asking how many years of data you've gathered.
I believe we'll have 10 years of data of honey production associated with weather. And then the Environment Canada database is immense. You can go back, if I use Montreal as an example, I think you can go back 100 years.
Wow,
So any type of trending in temperature, severe weather events, rain, humidity should all be there.
Incredible. And we have a follow-up question from that. Someone is asking, how do the years of data in the different data sets align?
That's a very good question. I think, I'm not sure if I understand the question totally, but if you're looking at, for example, honey production that goes up in kilos, for example, that would suggest that if it was the spring, you had good conditions. So what were those conditions that made that go up? And conversely, if it was down, what are the conditions that made it go down? And maybe there's some correlations that can be made between drought, lack of rain for 2 or 3 weeks, too much rain for 2 or 3 weeks. And if that can be shown then over years, then that's what I mean by a predictive model.
Fascinating. Thank you so much. To everyone who's listening, if you have any other questions you'd like to ask Chris now, please place them in the chat or in the Q&A function.
I should mention data that I've just received from many people with urban bees. It's a new field. The urban bees are doing very well, and in some cases better than the ones outside. So there's all kinds of data points that we don't have time to talk about today. Competition, location, availability to water. But maybe there's something even that could be teased out that we'll see that might suggest good conditions in cities. They tend to stay warmer at night, for example, than the surrounding areas because of the concrete, the heat island effect. So anything like that could be talked about, and I'll be available to try to answer some questions later today and during the week.
Wonderful. Thank you so much. That would definitely be a very interesting area of research, looking at how the urban bees differ from the rural bee population. We have one last question that just came in. Is there a similar commercial data set?
Yes, we tried to get some and we could not. Some of it is proprietary, so we get into the whole open source part of this. But there are companies that are doing a lot of using AI. There's sensors in every hive, and they come with a tractor trailer. 200 hives go out, and they're actually cataloging how many bees are going in and out at any given time, how much work they're doing, which is really important if you have several thousand apple trees or hundreds of acres of strawberries or peaches. So AI is now a big part of pollination, but
Yes,
we don't have
wow.
that data with us this time. Maybe next year.
Hopefully soon. Yeah, hopefully for our next hackathon. I think we have time for one more question. So in just a minute or so, how much data is there from before the bee die-off compared to afterwards, and are there differences?
I don't know what that means. Bee die-off. If you look at the honey production, the healthier the hive is, the more numbers. In other words, more workers going out and foraging means more honey. So that I think for this hackathon, what we should be focusing on is the weather conditions and then the honey production as well. If the honey production is going down, something's wrong inside the hive. Now we can correlate that to weather. It might be disease, for example, but disease can also be correlated to really high temperatures. If they get under stress like we do, and like any living creature, when stress is high, disease sets in. And it's also weather dependent. So I'm still very interested in, if you're telling me there's more heat waves in the last 20 years compared to the last 50, that's really interesting to know, because then we can anticipate more issues with health of the hive.
Absolutely. Yeah, it'll be very interesting to see how AI and our other technological advances can help us gather more information and answer these fascinating research questions with it. So
right, and I may add, these very questions are exactly what I would like to know. I do not have the human capacity to go through 100 years looking at 1 or 2 data sets and making a correlation between that, but to have that, to use AI to actually collect that quickly and say, yeah, there's a definite trend happening in the last couple of years that may affect bee activity, that would be really interesting for a group to present in 48 hours.
Definitely. Thank you so much for your quick but very thorough introduction. And I'm sure I can speak on behalf of everyone. We really enjoyed hearing from you. I think it's time to pass it off, but if Timothy or Monika would like to come on and introduce our next presenter, I will hand it over to them. Thank you again for your lovely presentation.
Thank you, and good luck to all the participants.
Amazing. Thank you so much, Chris, for that. I didn't realize how much work 1 spoon of honey required. That's amazing. I think there's a lot to learn from this data and from this challenge. So let's introduce the next speaker or next challenge, which is the wind energy prediction. So this challenge is one of the 3 Kaggle-style challenges, and it takes 2 climate approaches, both adaptation and mitigation. So without further ado, I'll introduce Bo Cao to present this challenge. And just a reminder to ask your questions directly on the live feed so that we can answer them at the end of this 15-minute segment.
Thank you, Monika. Yeah, I probably share the screen. Okay. Thanks for everyone. So very pleased to attend this impressive event. My name is Bo Cao from the University of New Brunswick. So today I will bring the challenges, the titles, the wind power production forecast with limited historic data. So here is the brief outline today, including the background motivations and the Chicago computations and a Q&A session. The first things I would like to introduce the background and the motivations why we have these topics or these challenges. Actually, it's in the past a few years, 5-6 years, the University New Brunswick have been founded by the NRCan, focused on converting the public national methodological wind forecast produced by Environment Canada into a format which the utilities could be a benefit. Actually, is that I think that everyone has already know the wind is one of the most promising renewable energy source, and the installed wind power capacities even in Canada has the sustainable steady growth in recent years. I believe so the wind is probably is the second most important renewable energy source. But we know, like due to the natural variabilities of wind, the integrations of wind energies into electrical power systems is a challenge. The variable and fluctuating wind power caused quite a lot of problems in power quality, system stability, and energy dispatch. All these problems becomes more and more severe, becomes more and more worse. Along with the penetration level of wind energy is increased. Therefore, so it's desirable to have an accurate wind speed and wind power forecast to provide that service. So in that product, we have a cooperate with the Environment Canada, ECCC, NERGICA, and we can quite a lot of partners from the different institutions, and our focus on the forecasting service about the short-term wind power production forecast for large wind farms, medium or large scale wind farms, the wind power ramp forecast and the icing forecast. Here's during this project, actually, we developed the UNB developed wind forecasting package. It's a free to any wind farms in Canada to use. But when we talk with these wind farms management or wind farm owners, we found a very key problem is like because normally we use a data-driven method to produce the wind power production forecast. They need historic data, but even the wind farms that has some historic data, and they found it's very difficult to implement into a training process. Even in our softwares, we have online trainings part, but it needs even 3 to 6 months to complete the training. That's not good for the utilities and wind farms operators. So that's my questions coming up. So I'm thinking, like, because in the past few years, we have already investigated quite a few wind farms across Canada. So, and we collect quite a lot of data, so historic data, so from these wind farms cooperated with the utilities. So we have the source wind farms, and we have a good wind forecasting service. But for a new wind farm, one new wind farm coming up, a new client, new user, even the existing wind farm, but just goes through a new update, like put more wind turbines there. How we can put how we can offer the forecasting service to the wind farms without, or they just have a very few historic data. That's my question. So I'm thinking, like, if we can use the AI or deep learning method, like transfer learning techniques, to make solutions to that. That's my question. And normally, like the one of the challenges, like the layout of the different wind farms. For example, here is a line, like all the wind turbines in a line with a grid or just group. I provide some examples. Here is a line layout wind farms in Alberta. Here is the grid ones in China, and there is the group ones in PEI. But in this make it the forecasting transfer abilities even more challenges. But in these competitions, we just assuming the target wind farm and the source wind farms are have very similar layout. So the objective of this cargo competition is like to generate hours ahead wind power production forecast. Like we need to generate the wind power productions every hour, but with look high times from 30 minutes to 6.5 hours with 5 minutes time steps. That means like we need to forecast the every hour to provide the power production forecast in the following 6.5 hours. We have a two wind target wind farms. Wind farm 1A, which has 1 year's historic data, but another ones which has a similar layout, but they only hold 1 month's historic data. So for every team, so the input of this question is hourly wind speed and wind directions forecast up to 48 hours ahead. So you have the wind speed and the wind directions for each wind farms up to 8 hours, but it's just hourly data. Like you may know the next 1 hours, next 2, next 3, up to next 48. And output, we hope that you can get a very accurate wind power productions predictions up to the next 6.5 hours. And we need to, the whole forecasting mechanism is you need to provide the forecasting service every hour. Here is I just introduced the data side I provide. We have 2 wind farms. One is wind farm A, which have the maximum capacity is 45 megawatts, and another one is 99. The dataset one, all the data is raw data, is from the realistic applications. So you may have the missing values. So you probably have you probably can missing values, even errors. That's possible. So imputation methods may need for your processing your data first. And here's we have 3 data sets. One is 1 year historic data of hourly wind speed and wind direction forecast, which of a wind farm A, which used to produce the forecast for wind farm A. It looks like including time steps, wind speed forecast, hourly wind speed, and wind directions. And you also have the measurement data with higher time resolutions for every 5 minutes, including the available megawatts. That means like sometimes some of the turbines in wind farms, they may just doing maintenance, so it's not account for the total capacity. But everyone needs to pay attention about that, because this one is normally using manually update this number, so it's slow, so it probably not correct. It's just for your reference. But you have the wind speed and wind power. The data set 2 is for wind farm B. You only have 1 month historic data, similar to the data set 1. And the data 3 is you have a 3 months historic data, so wind speed and wind directions forecast for your testing. So I believe that the chart will use that, the data set 3, to evaluate your result. And here I provide some global, very common global statistical metrics like Bayes, mean average errors, root mean square errors, even mean absolute percentage errors, to evaluate your result. In my opinion, it's just like I think the MAE probably have a higher priority than RMSE or than MAP. That's in my opinions, but it depends on what the judge thinks. That is basically my introduce of my questions.
Thank you.
Yeah, probably.
Thank you so much for that presentation. I'm just gonna ask all participants if they would like to share any questions that they may have from this talk. You can put them now in the chat. If not, if people don't have questions at the moment, you can always ask them in our Slack channels later. So the Slack channel will be available throughout the hackathon as a wonderful place for everyone to communicate, get in touch, and ask any questions they may have. I think a question has just arrived. The question is, how is the data collected and how clean is this data?
Excuse me, so my internet is not as stable. Could you just repeat your questions?
Yes, no worries. The question was, how is the data collected and how clean is the data?
Actually, the data is clean from the practical, all the wind forecast data we collect directly from the public models from Environment Canada, the ECCC as well. We just because in practice, ECCC would update the wind speed and wind directions forecast every 4 times a day. But for to try to simplify these questions, I provide all this with average functions. But if there has error, I just leave that error. So, and all the measurement data is from the utilities. That's like from the wind farm itself. So it's from their measurement. So it's also from practical. So I don't put any pre-processing or imputation method to them. So it's pretty close to a practical case.
Wonderful. I believe that is all the time we have and all the questions. Oh, one quick question has come in. So let's see if we can answer this really quickly. Mm-hmm. Are there 2 parts to this challenge? One to predict the wind speed at the farm and the other to predict the power output given a wind speed?
I actually said the wind speed forecast probably your intermediate intermediate, I'm not use that to evaluate result. All my result is I would like to see how the wind power production is forecast. So you probably to try to build a direct link between the wind speed forecast to hourly wind speed forecast to the power, or you probably use the wind speed forecast to your wind speed forecast to the wind power productions. It depends on the teams.
Perfect. Thank you so much. For anyone else who has a question, we're going to ask you to please place those into the Slack channel, and hopefully we'll get back to you as soon as we can with that. In the meantime, thank you so much, Bo, for that lovely presentation.
Hope everyone enjoyed the event. Yeah. Thanks.
Thank you. We look forward to hearing more from you later.
Yeah. Thanks.
Great. Hello. So
wait, hold on. I'll just introduce you, Stuart. I was waiting to be unmuted. So thank you so much, Bo. I'm really impressed that wind energy in Canada could be a high potential. So thank you for that. And without further ado, I want to introduce you guys to the third challenge, which is the Challenge AI Art, which is a special category on its own, the AI artist, and tackling awareness. And I'd like to introduce Stuart Spence, that we have here and that you've seen him probably on Monday, with his colleague Simon Demerle. So the floor is yours. Sorry, go ahead.
Great. Thanks so much. Right, so the AI Artist Challenge. For this challenge, this one's coming from Environment Canada. That's where I work. I work in the supercomputer with the weather forecasts. The AI artist is going to be where you create a system that artistically interprets data from any of the hackathon challenges, any data that we've seen. And we want to create beautiful data visualizations, music, abstract images, or unique pieces of art. And you can, like I said, use any data from the hackathon challenge, but if you specifically use Environment Canada data, then you can benefit from the technical support of our Environment Canada mentors. And as you may guess, this category is judged subjectively because it's art after all. So we're trying to raise awareness. So whatever you think would best raise awareness. And we could go to the next slide for a quick rundown on some of the requirements here. And you can ask me, Stuart or Simon, about any of the requirements if you have questions. But basically, it has to be digital. So this means the AI artist runs on a computer. You can't just write instructions on paper or something. It has to be dynamic. So you maybe use today's data to make your art. But if tomorrow you got new data, it wouldn't be too much work to make it work for tomorrow. It should be explainable. So you can explain how your AI artist is using climate data to make the art. And viewers can at least sort of see the connection. It's not just like, here's some random abstract piece of art and we just can't even make a connection to climate or data. That wouldn't work. All hands on deck. So you can use any software and you can write new software for this challenge. However, for authorship, you can reuse existing code, but for your submission, you have to make it clear what code you wrote before the hackathon, what code you wrote during the hackathon, and what code you did not write but got from somewhere else. And the focus is mostly code you wrote during the hackathon, but this is 2021, so you're going to be reusing a lot anyway, we're sure. So that's everything on the requirements. If we go next slide. There is one game called Radio Sound Can on the Google Play Store. And this is something I developed 2 years ago for hiring events and conferences. So you can have a look at this. It is open source. It's on the Play Store. You can see it on GitLab. It was made with Unity 3D and C#, and it uses real wind data, and you can spin around the globe in 3D. So that's kind of one just interesting example maybe of art, but that's just one, because we have Simon now coming up, and he's going to tell us about some of the art that he's working on too.
Yep. So, hello everyone. My section of the presentation is going to be a bit around what I'm making, kind of as an inspiration for maybe what you could do, and also just kind of an overview of what AI and art have in common together, what they bring together that's new, and some of the points you might want to put attention towards in trying to make something interesting this weekend. So just a tiny bit about me. I studied computation arts at Concordia. I'm doing my master's in artificial intelligence at University of Montreal, and I'm also lecturing there about digital arts. I have both kind of a background in formal computer science and fine arts. So the main question I'm bringing with this is, how does AI change art, and how is that interesting, and how can it affect what we make with AI and art? And one of the main points is AI is really different from any other method you have of playing around with data or just creating digital art. Because you're not, unlike classical algorithms, you're not deciding, okay, this is the exact precise process I'm going to be using to create that thing. You're kind of just deciding that you want a general structure for some kind of task you're designing, and then you let the data figure out, well, through training, you let the data kind of finalize, crystallize how this thing is going to work. So you can inject some kind of meaning or some kind of structure from the information you have as data, and that's interesting. One of the very obvious things it leads to is it kind of opens up the door to a new aesthetic, because it's not you that's deciding on a style for how you're creating music or visuals or whatever it is you're making. It's kind of the data that's creating it for you, and also the structure you decide to give your models. So a super kind of cliche example of this is Deep Dream. And it's interesting because it's not like someone sat down and decided to paint it that style. It's a machine that came up with this. And somehow, because it's structured in a certain way, and because it absorbs some kind of data that we're familiar with, we are seeing some familiar patterns in this. And it's interesting, and it makes us feel weirded out, and it's creepy and strange. And that's interesting. And another thing is style transfer. So you've probably heard of this also. And like there's the obvious aspect of, okay, that's cool, I can transfer an artist's style, and that's aesthetic. But besides this, like there's a super postmodernism like interpretation of this, where you can borrow the style of an artist, and by doing that, you're linking yourself to that artist. And then you can link yourself to, okay, what is the question that this artist is asking? What is their philosophy? And how does that relate to what I'm trying to express, or the questions I'm suggesting in my art? And that's an interesting path too. So another thing is AI is not static. AI can be dynamic, and it can open up the door to certain kinds of interactions that are not possible otherwise. And I'll show you such a thing with my example with text and dialogue. And the other super interesting thing about AI, and this is pretty much true of all mediums for art, is that art and AI do not exist in a vacuum. They exist in society, and they are really reshaping the way the world works right now. And by using AI in your art, you're using these technologies that are changing our world, and you can look at what's problematic or what's good or what's bad, and you can suggest some paths for reflection about these things. Some very obvious examples are, for example, on social media, on Facebook, on YouTube, on Instagram, all of these platforms, we get shown some content. And there is AI that decides what we get shown. And the thing is, we know that there is an issue with this actually, because radicalizing content gets shared overwhelmingly in some cases, and that leads to some of the political issues and political tensions we have right now. Another example is ethnical bias in data sets for facial recognition, for example, which has been partially addressed. And obviously, we're here talking about climate change. So there has to be some kind of question you can ask or suggest through what you'll be making, which would be an interesting path for reflection, besides just what is the surface level of what you'll be presenting? What does it look like? What does it feel like? And the other one, it's not so much a path for reflection right now, but it's just an exciting thing and kind of my stance on AI and art. And it's that AI, modern AI, is extremely young. It's only been around for about 10 years and it is constantly evolving. And if you compare this with other classical mediums like photography has been around for 200 years. If you compare this with sculpture and painting, it's been a few thousand years. So this is extremely young. There are many things left to explore and try out. And as an artist, that's incredibly exciting. So now that I've talked a bit about why I think AI is interesting and what can make it interesting and what you might want to pursue in creating your art this weekend, I'm going to show you one of the things I made that kind of exemplifies that or tries to play around with that in some way. And it is exploring interaction, aesthetics, and patterns in big data. So I will invite you to open up a web browser and type in whatliesahead.io. So the address is here, and we will see if my server crashes. So this is an art project I created with Pauline Pamal, who is a neuroscientist and language researcher and poet. And this was kind of an exploration of what can we do with big data in the context of text and literature, and what kind of interactions we can create with someone and a machine that's spitting out text. And we found that this was something interesting to explore because you're faced with a thing that doesn't have a clear intent, but is producing some kind of output that has some meaning that you can interpret. So you get to decide what it means. Sometimes it's absurd, sometimes it can sound profound in some way, and it's interesting. So I will show it to you live on screen, and you are very much invited to try it out on your own now. So I will read out the text for you. So what lies ahead is an interactive poetic experience. With the words you will offer me, I will weave you a poetic cloth. I do not know what lies ahead. You are my unexpected. I will try and pick up your threads and create my own patterns. After all, I do know Shakespeare, Whitman, and Virgil. I have studied them silently, relentlessly, like a silkworm building its cocoon. Connections have strengthened my network, sometimes arcane, sometimes playful. I am ready to talk to you. Are you? And now we get to type in things and see what happens. So what can we ask? Oh. So very much in the spirit of the conference right now, I have no clue what it will tell me. So let's see if it's absurd. So the answer we get is, in the days of old, when the stars were 100, when the moon was a single atom, when water was a breath, when air was a breath, and then we can just continue on and on and on. Calm. All right. I guess we can open it up to questions because otherwise I will just continue on typing things. And it's probably more interesting for you to play around with it yourself. So let me find the chat window.
Thank you, Simon. That was a really interesting explanation and kind of a trial run of the ways that AI and art can be woven together, and this, like you mentioned, youthful and constantly evolving new area. We had one quick question just before we have to pass it on to the next speakers. One of our viewers is wondering if, in your opinion, can aesthetics be explained in one word?
No. Sorry to disappoint.
No worries. I think we'd all probably have to agree with that answer. I think that would be a very challenging quest to take on. So Thank
Yeah.
you so much, Stuart and Simon. That was wonderful. And I'm sure people are very excited to start exploring what's out there and what lies ahead in this aspect of our AI Climate Crisis Hackathon. Now I'll give it back to Monika to introduce our next speakers.
If I can just add a tiny thing, we will stick around. So if you have any questions, if you want any kind of advice about AI art in general, I will be sticking around this weekend. So there will be a Slack channel where you can ask questions and book some mentorship session thingies. So
yeah, exactly. Thanks.
Wonderful. Thank you so much.
Amazing. Thank you so much, guys. I think it's super impressive, and it's amazing that we can really merge creativity into this climate change and AI hackathon. Thank you both for that. So moving on to the next challenge, so the fourth one of this afternoon, which is the challenge Reducing CO2. This one is a data visualization approach with the goal of raising awareness on climate crisis. So I'll invite Matthew Chapman and Dean to present this challenge. Up to you guys.
Thank you very much, Monika, and the whole team. It's great to be with you again. Nice to see many of you on Monday as well. So let's see if I've done that right. I believe I will have to share the other window. Okay, let's try that. Okay, are you seeing the slides change now?
Yes.
Yes.
Okay, great. So problem definition, I'm going to start with that. Obviously, climate change is the problem. Part of the problem is communication. Part of the problem is not understanding, how to take action effectively. And when you start shooting in random directions, you get people understandably upset and claiming that you're ideological in your willingness to take action. And it's very dangerous to take action without having data to back it up. And that's what this challenge is about. This challenge is about what you're looking at on the screen right now is what we have right now in terms of communicating climate data in communities we live. This is the best it gets from what I can find online. Among Canadian municipalities and even worldwide, it'll be up to you to find better or to make better than that. And the challenge itself, this document will be provided to you shortly by the organizers. And I'm going to take you through the 4 pieces of it, really. What data we have and why we're using that data. Questions that your visualization could seek to address, types of data visualization that are possible, and tools that you could choose from to conduct those visualizations. Climate Reality has 30,000 members across the world whose objective it is to communicate data. So what you're looking at here is the data set that we've provided for this challenge. And data, unless it is communicated effectively, can be dull, can be boring, can be not very engaging, particularly for the average person, and maybe a little bit, that might not be as true for the audience that we have today on this call and at this hackathon. But until you do something with the data, it's a little bit mundane. Either one, create technology to leverage it, or create a narrative, create a story, communicate information that helps people better understand it. So here's the data set we're looking at. And this is what we are faced with right now, currently, when it comes to how is my city doing on climate change? Okay, and this is what we get. And most people are going to close that book, close that window and move on to something else. What we'd like to move towards is applying the best practices in data visualization that exist for other issues and at the global level for climate change, and apply some of those best practices to the local level where people live, where people have relationships, where people have memories and feelings and moments, because then you're tying this global issue to a very visceral and real space in somebody's life. Really important sociologically to do that. And so far, we haven't had the wherewithal, capacity, motivation to put the effort into localizing data visualization around climate change. So here are a few visualizations that help us at the global level, interesting ways in which we can use this data that the Carbon Disclosure Project has collected to create engaging visuals. I'm not sure if can I ask questions of the audience now? Can I ask people to raise their hands or interact? How does that? Would it be
Yes,
the
you can
Q&A or the
definitely
chat?
ask.
Yeah. Okay.
We'll do our best to facilitate between the audience and yourself, but
Sure.
go ahead.
All right. So this being one of the first examples of a data visualization that tells a story. And it's a very easy answer, so I'll just ask for it. Who can tell me what story they get from watching reams and reams, 100 years plus of climate data? Who wants to have
So
an easy
to
answer?
everyone participating, if you'd like to answer, maybe you could just type it into the chat just so we don't have to struggle with unmuting ourselves.
Sure
But
thing.
yeah, please feel free to answer this question in the chat.
Thank you very much. All right. So there you go. You don't, it tells you a very clear story that yes, it's getting hotter. And that's what we need to do to bring people to the realization that in my city, in my community, that place that I call home, the place that I care about, bring that kind of, revelatory realization that we need to do something about this. A few other visualizations that you might choose to draw inspiration from. These are all GIF illustrations, one of the 5 types that I'll be looking at in this brief presentation. GIF illustrations such as sea ice over the course of several decades, shrinking and shrinking and shrinking. This one I did show on the other on Monday's call, so I won't belabor it, but as you can see, the GIF here is sped up quite a bit. So these first 3 are GIF-based data visualizations. You might consider learning how to use Jiffy or other online software tools to create this type of visualization using the data that we've provided, or that the CDP has provided, rather, Carbon Disclosure Project. Here's another example of an animation. I believe this was created, by visme.co, and this is another platform that anybody interested in data visualization would do well to understand and to practice with. So, and pardon me, the purpose of this visualization might not have been as clear as the last couple. This is the coastal sea level change across the United States of America from 1960 to present day. So in what direction is this trend moving, essentially? And we're seeing quite dangerously moving in a direction that is going to make the coastal real estate of the United States of America uninhabitable or very expensive to pump dry in the next couple of decades. Here we have another type of visualization, another animation, a little bit drier per se, not as visually beautiful perhaps, but delivers a very stark message nonetheless. So we have the global carbon budget as represented by the entire square, and then what's left over on the right-hand side, what's been consumed in the last decade in that slightly lighter purple rectangle there it is. And then basically what we should be aiming for in the next 3 decades in order to respect that global carbon budget. So yeah, another example there of animation-based data visualization. This is infographic type data visualization. So it's not perhaps quite as relevant to this audience, but you're more than welcome to explore this direction as well. And this can often tell yeah, it's a different medium to tell a slightly different story. And there are a number of the tools that I'll be presenting shortly that will allow you to do that kind of thing without having to pay for a license, for example. Yeah. Lastly, charts. So your typical charts, these can be interactive where you roll over them and the name of the country pops up. This one is not interactive in that nature. And this demonstrates the vulnerability of a country on the y-axis, and on the x-axis, the extent to which the population is growing. So you'll see that the countries that are at extreme risk down near the bottom of the y-axis are also the countries in general that are growing the fastest. And tend to be, pardon me, in Africa and Asia. Finally, I believe, yes, finally, in terms of the types of visualizations that you might want to jump into, we have this type where you would create a kind of a one-page scrolling web page where you can play around with the page and explore the data more deeply. Dig into, okay, this city is doing this city is doing that. That becomes an option as well. And finally, I'll just run through 5 or 6 options you have in terms of the tools that you'll be working with, learning with, and developing, cutting your teeth on getting better at taking data and making it meaningful, essentially. So there's Visme. I mentioned earlier a couple. I think the one with the sea level rise was Visme. This is also produced with Visme. What's called, I think, an energy flow chart, but in this case, it's dollars flowing from donor countries to recipient countries that are needing to adapt rapidly to climate change. Venngage being another one, and all of the links to these are in the 2-page challenge description. Canva.com, also a very usable alternative to Photoshop for doing simple design, for conveying messages, particularly when it comes to the data visualization, pardon me, the infographic versions. Jiffy to create GIFs, and Tableau to get a little bit more, a little bit deeper than the other ones permit. So to recap, before we go to Q&A, the challenge will see you take this data here and communicate one of the questions that have been proposed here. Which cities are the most transparent with their climate data? Which are shrinking their carbon footprint fastest? Which have the lowest per capita emissions? What relationship exists between data transparency and emissions reductions? You might also decide to go further than what's available in the first tab of this, this chart and go into some of the deeper data. The first tab has been cleaned up so that it's easier for you to work with. And you might choose some of these other questions. And then finally, you might even go further to correlate, draw some correlations between the data that's provided here and other data sets online, including the National Climate League, Stat Tracker data, and others. So I'll wrap it up there and take questions about this challenge.
Thank you very much, Matthew. I'm just quickly checking in if anyone wants to post their questions now. So far, we haven't gotten any. I would think it was a very clear, very broad presentation. Definitely introduced me to a lot of new data visualization techniques. So thank you once again for that. Just to remind everyone, if you don't have questions now, but they come to mind later, please post them in the Slack channel and we will do our best to connect you to the speakers or answer them ourselves. It seems that we have a few questions coming in now. So someone would like to know how we can access the Google Doc. I believe you'll be sharing it with us.
Yeah, it's here in the chat now.
Wonderful. So that should be there in the chat now for everyone who needs access to it. We also have a question asking, what types of audiences are you targeting with this data? Are you looking at average citizens, elected officials, etc.?
That's up to the teams. We haven't specified. You'll see in the two-pager that the criteria by which we're judging the documents are aesthetics, so how beautiful, clarity, are you telling a story easily with what you've put together, interactivity, if you're able to do that, and if the tool that you've chosen permits you to do that, and finally, virality. If this posted in a public space, are people going to pay attention? Is it going to get is it going to attract attention on social media, for example? So in that case, it's probably in your best interest to make something that is largely comprehensible by the general public, but it's not required.
Perfect. Thank you so much once again, Matthew. It was lovely to hear from you. And now we're going to move on to our Sea Ice Challenge. So I will let Monika introduce our next speaker for that. Thanks again.
Thank you all.
Thank you so much, Matthew, for showing the power of visualizing data and making it a very powerful message. So you will all be able to work on this challenge that was the reducing CO2. Now let's introduce our next challenge before we take a very short break and move on to the other four. Our fifth challenge today is the Sea Ice Movement Challenge. This one is another one of a Kaggle style, but also the choice to do data visualization, and it really tackles adaptation. So without further ado, I'd like to introduce Charles Brunet from McGill University to tell us more about this challenge. Charles, the floor is yours, or Charles, sorry for giving a little Quebec edge on your names.
That's fine, both goes. Charles is fine. I'm a French speaker, so during the weekend, if anyone has a question, I can do both French and English. That is fine with me. I hope you all hear me all right. Be sharing my screen. Can you see my PowerPoint?
Yes.
Awesome. So I'll get this started. Okay, so yes, thanks for the introduction, Monika. My name is Charles Brunet. I'm a PhD student at McGill University, and my research focuses on sea ice in the Arctic Ocean. So this, in a nutshell, this project is about, we're asking you to use an AI approach to produce estimation of ice motion, ice velocity in the Arctic based on wind fields as a forcing data and other different parameters that you can throw in the mix. This is some research I'm currently working on for my thesis. So if that's something that's appealing to you, that sounds good. Well, it's actual research. It's not a test data set or a solved problem. It's an actual research, a dynamical live research problem that we're interested in. And we're curious to see how creative you can get with an AI approach. Disclaimer, I am not a artificial intelligence machine learning person. I have limited knowledge on that question, but yeah, we found that the data set I was working in was almost AI ready. So we're happy to be presenting it in the context of the AI hackathon. And thanks for the AI Launch Lab in Montreal for inviting me to present this project here. All right, so sea ice, the Arctic system is particularly interesting, right? You have this fascinating Earth system where you have the ocean and the atmosphere interacting together, and in between you have this part of the frozen ocean, sea ice, and apart from this just Earth system, you have a biology system that's on top of it, and you have humans that live in coastal communities around the Arctic. So you have this very intricate and that has a very intricate equilibrium in this Arctic system. And any perturbation to that system has major consequences. So we know that not only is this Arctic system warming up, well, there's a phenomenon of Arctic amplification, right? So 1.5 average degree of warming on a global scale is amplified 2 to 4 times in the Arctic. So that means 3 to 6 degrees C in the Arctic over a long period of time. Here you see the Arctic amplification and 2014 2018 period compared to the 1950, 1980 baseline. So you see how major that amplified warming is in the Arctic. And that has very remarkable consequences, right? I'm just throwing a video here that shows the dynamics of sea ice, how sea ice evolves over time on the monthly resolution. And it's a cool video because there's many types of variabilities happening at the same time. You see that shrinking and expansion of the blue colors. That's where there's sea ice. That's the seasonal cycle of sea ice, right? The sea ice is at its minimum extent in the summer, where it's always bright and it melts, and it expands in the summer and the dark of the polar night. So you have the seasonal cycle. On top of this, you can see, right, there's some movement. The ice moves under the forcing of the atmosphere and the ocean. So it's a very dynamic system. And you see how much, right, over a year, over a season, how the ice is dynamically driven and moving around. And I don't want to show the whole video, right? But if we skip to the next slide, that shows the difference in between the minimum sea ice extent at the beginning of this satellite record in the 1980s and the minimum sea ice extent in September 2019. You see the striking differences, right? And one of these differences is kind of obvious, is the reduction in extent. It was nice from the last presentation from Matthew to already point into that striking visuals of the sea ice as an indicator of climate change. You see that reduction in the extent, but on top of this, you have a massive reduction of the thickness of sea ice. The color scale here from darker blue to white shows the age of sea ice, which is also a good indicator for thickness of sea ice. Older the ice is, thicker it is. So you see how much over 4 decades, we've lost that thick ice, and how those two factors, the reduction in extent and reduction in thickness, they've had massive implication for the motion of sea ice and the dynamical response of the Arctic system. And that's where we're interested in studying. So we have a little tool. I hope, can you guys all see my browser?
Yes.
All right. So we have this tool, which is called the Sea Ice Tracking Utility, that allows you to place artificial buoys in the Arctic and calculate trajectories of sea ice. And you can apply this to many different climate-related problem or environmental problem that you could think of. Say there's an oil spill near the Russian coastlines, and you would want to know where the ice is drifting because it carries with it some oil from that oil spill. So here in this software, you can look at the drift of ice over a defined period of time. So let's go ahead. If I put a tracer near the Eurasian coastline, say there's an oil spill there, you will see over a period of, here we're calculating 24 months, how that pollutant would be transported by the drifting ice. And you could test it for many different regions, and they all are representative of the historical motion of sea ice. So that is a kind of very powerful and interactive way you can try to think about problem related to the Arctic climate, but in terms of its dynamics of the ice moving. But to do these kinds of studies, what they rely on is information about ice motion. And where do we get ice motion in the Arctic? You have drifting buoys in the Arctic. So there are literally GPS tracers that are on the surface of sea ice and drift. So they're very precise. You can get information about ice drift from satellite. From satellite imagery, you can reconstruct ice motion. And if you have none of these, you need to make an estimation. Just to show you how these estimation of sea ice are important, this figure shows a map of the Arctic, and the blue dots correspond to where you have satellite drift estimate, and the red points correspond to buoy data over 1 month. It's all the data compiled over 1 month during the summer. Some satellite instruments have less sensitivity, so don't return ice motion vectors. So you have gaps in this data set. So you need to make the most reliable possible estimation of ice motion to fill the gap and produce seamless data set for ice velocity that then help us do those studies where you can track motion of sea ice. I don't want this to get mathy, but like it's a very simple equation just to give you a feel of how we can approach this problem in a very classical way, right? So we have this, from the physics, you can derive this relationship where you have a linear relationship between UIs, the sea ice motion, the sea ice velocity, related to UA, the wind velocity, plus a contribution from the ocean current. And the relationship between the ice velocity and the wind velocity is moderated by a coefficient, a wind ice transfer coefficient. So it just converts the velocity. This usually takes a value of 1 to 2%, right? It's in that range. You have winds from meter per second being transferred to ice velocities of centimeter per second. And you have a complex exponential with an angle that does a turning, because the ice drifts to the right of the wind motion because of the Coriolis effect due to the rotation of the Earth. So that's a free drift case, what we call the free drift, a classical representation of wind-driven ice circulation. And here what we're asking is, well, what can you do with AI, tackling that problem differently, maybe representing maybe higher order relationships between wind motion and sea ice motion that we're not representing with this linear equation. How good can you produce those estimates of ice motion? Yes, so that's what the challenge is about. The data you have, we have a program that collected, there's the International Arctic Buoy Program was compiling buoy drift data for the last 40 years. So we have a long record of drifting buoy data point on which we have co-located different parameters such as the wind speeds, the sea ice concentration, ice thickness, different sea ice state parameters. So your task here is to take the wind velocities and transfer them into sea ice velocities using the different parameters that we're providing to you. Right? So very schematically, like in a simple schematic, that's what we're asking from you. We'll have a quick look at the data. So you see this is a list where every entry is a buoy point. And for how this data is organized, you have a timestamp for each of these entries. You have the location of these data points in Cartesian frame of reference. You have the information derived from the buoys about the ice velocity. You get, for the same location, the information about wind speed and a bunch of sea ice state parameters that can help you better represent this wind to ice relationship. So we're providing you with two data sets. You have training data set that has over 300,000 entries from 1979 to 2019. So you can build a model that will, again, transfer the wind into sea ice velocity using the different sea ice state parameters. So you have this training data set, and we've provided, we're also providing a test data set that has, well, we split it 80% for the record and 20% of the record for the testing data set. So you have these two data sets, and what we're asking from you is, using the test data set, return us a list of components of ice motion that we will then compare to observational buoy ice motion. And the evaluation is rather simple. How good is your estimation of ice motion, right? So if we look at those two vectors here, you have, say, your ice motion estimate in the solid line, and the dashed line is the observational buoy motion. How can you reduce the error on the speed and the error on the angle for those two vectors? So we're looking for the minimal root mean square error on the total speed and directional error. So that's the purpose of this Kaggle style challenge. In terms of data viz, I don't know, it slipped to the top of the challenge. It's maybe less oriented toward data viz, though. If you're interested, you have buoy points in the Arctic, and you can convert these back to geographical coordinate and do spatial representation of this information in the Arctic. So if you really want to do spatial visualization in the Arctic, that could be interesting to look at, an interesting data set to look into. But yeah, otherwise, I think that the primary purpose is really how can you, is really for you to make the best model that reproduces the ice motion based on the wind fields. And if you're successful, it's something we're interested in working through with you and potentially opening up collaboration with our group at McGill University. So that's pretty much it. You can contact me at my email address over the weekend. Otherwise, I'll be monitoring the Slack Challenge CI channel if there's any specific question pertaining to the data specifically. And I guess we have maybe a few more minutes if there's any question left from the audience. But thank you so much for listening. Looking forward to your creative solution to that problem.
Thank you so much, Charles. That was so captivating, and it's almost frightening to see the outcome and just in the same generation, how much the sea ice caps have been melting. So definitely a challenge that has lots of meaning and needs lots of attention and action. So thank you for that. I'll be taking maybe questions if there are any from the chat, from the audience before taking a 5-minute break. So let's see if there are any coming through. And once again, I want to remind you guys that there's a Slack channel for every challenge. This one, the sea ice, is the one where you can find Charles and ask him questions through the weekend. So we have one, Charles, maybe for one question before we move on the break. How are we using the buoy, sorry, my accent, data, but not the satellite data? So how are we using the buoy data, but not the satellite data?
The idea here is the buoy data is your most reliable source of information about sea ice drift speed. So we take the buoy as true. It's very precise. It's GPS, right? So it's very precise. So we want to train on this truth data set. Satellites have biases, have limitation in how you retrieve ice motion. So they are very useful. And at the end of the day, we want to make a merged data set and use them all. But in terms of training, we really want to focus on the buoys that are the most accurate representation of ice motion.
Perfect. Thank you, Charles. So I think we're running out of time. So guys, we'll put on the screen the schedule for today and see you guys at 3:50. We have 4 more amazing challenges to show you, plus 4 keynote speakers. You guys don't want to miss that. So take a little bio break, coffee break, whatever is your poison, and come back at 3:50, so in 3 minutes.
Yeah, thanks so much to all the presenters. See you in a few minutes. Hey everyone. So we're back. And next challenge we have is hashtag sewage overflow. And we're really lucky to have the amazing co-founder, Nasen Saran. Nasen, are you there? There's
Yes,
Nasen.
can you hear me?
Yes.
Hi, everybody. So very happy to be here with you today and to present our challenge. I'm just going to share my screen. It's not going to be too long. All right. Please let me know if you can see my screen.
Yeah.
Yes.
Okay, perfect. So the challenge we're presenting at Can Forecast is to try to see if we can use climate data to try to evaluate the impact of climate change on sewer overflows. And so the first question you may wonder is, what are sewer overflows? So combined sewer overflows is a phenomenon that's not very well known by the general public, but it's very real. It's something that happens in especially large cities across North America that were built prior to the 1950s, I would say. So the way these cities were built, just to give you an example, Montreal is one of them, Toronto is one of them. The way these cities were built in the past is that it was the same sewage pipe that was taking water both from housings and from the industry, and also from storm drains. So whenever it rains, it's the same pipe, the same water that goes there. And that same pipe was directly linked to sewage treatment facilities. So this is the case in Montreal, this case in Toronto, in other municipalities as well. And so what happens is during dry weather, this is not a problem in general because the pipes are created in a way that the sewage treatment plant can actually handle the incoming capacity in terms of flow. But it becomes a problem when it starts to rain, because then, as you can see, you still got your sewage from housings and industry, but also you're going to have the rain, and especially when there is a storm or something like that, there is going to be too much input to the raw sewage treatment plant. And because the plant has a maximum capacity, once the capacity that the plant can handle becomes too little compared to what's going into the plant, automatically whatever is left is going down the river. And this is very bad because this is the same river that you and I go kayaking, go swimming in, go fishing in. So it's a direct consequence of how in certain cities, because of the way they were built in the past, weather can directly affect the quality of the water surrounding us in the environment. So the frequency and magnitude of overflows is directly linked to precipitation events, as you can see. So both in terms of duration and in terms of intensity. So you could have either a precipitation event that lasts for a long time and eventually it becomes too much for the wastewater treatment plant, or you could just have an event, a storm event, short but pretty intense, that's going to create the same situation. So as you probably know, this is a problem with climate change because climate change is going to impact how often we're going to have these storm events, the frequency of the events, and also the amplitude. So we could have a lot more water dropping at a certain area in the city and creating these situations. So the challenge we have for you, if you want, is to try to use past weather data to try to model the effect of precipitation on sewer overflows in Canada. And also, maybe if you can explore the impact of climate change on sewer flow variation in parts of the country. Specifically cities, that would be interesting because cities are the, as I told you before, cities are the communities that have this type of problem. So in terms of the data sets available, I was also told by our partners at Environment Canada that they have some data sets available for you in terms of precipitation and climate. In terms of the sewer overflows, I wanted to show you a few interesting links online. I'm going to stop sharing and reopen in a few seconds, sorry. Okay, can you see my new screen?
Yes.
All right, perfect. So first off, an interesting map. It's by Fondation Rivière in Quebec. It's a nonprofit. So they actually took the time to map out the entire province of Quebec, as well as historical sewer overflows. Just can you let me know if you can see the map right now? No?
Yes.
Yes.
All right, perfect. So here you can either click on a particular area that you're interested and have access to that historical data of sewers. Or you can also search directly for somewhere that you really want to model. Let's say, let's take Montréal Est. And then as you can see, you have the sector that you're particularly interested in, and you also have all the areas where you would have sewage coming up. This is one of, I think, the most interesting data sources for sewers. The other, of course, the inputs are mainly precipitation. You could also explore other data sets if you think they're relevant, like temperature, tides, depending on where you are. Towards Quebec, it becomes interesting to consider tides. You also have directly environnement.gouv.qc.ca, which is a website. If you have any questions for me, I'm going to put my contact in the chat. Feel free to send me an email. I will see if I can give you more information about how to navigate around this website. If I can, they have a lot of sewage data as well, historical. And this is another interesting resource for climate data. Feel free to check it out. So for this challenge, it's mainly trying to find correlations in the past and see if you can predict into the future. So how the increased frequency of precipitation is going to have an impact on the quality of the water over rivers and lakes in which we swim. All right, so that was all about the challenge. If you have any questions, I'm available.
All right, thank you so much, Nathan. That was great. And I think we are running a little bit low on time. So what we can do for questions is participants will be able to ask them in Slack. And I'm not sure if we've invited you to Slack, but we'll try to forward them to you through some other way if you're not on Slack. So thank you so much, Nathan.
Pleasure. Happy hackathon.
Yes, happy hackathon to all the participants. And thank you. So next up, we have Jean-Simon Venn, who is a co-founder and CTO from Brainbox, and he's going to be discussing the Challenge Smart Building. And Challenge Smart Building has two, I guess there's one type, so it's a data visualization challenge, and the climate change approach is adaptation. So let's go to Jean-Simon.
Hey, good afternoon, everybody. Thank you, Timothy, for the introduction. So I will present our challenge. It's a challenge that we put together between Brainbox and What Time. And what is What Time? What Time is an ONG NGO based in California, which is tracking the cleanliness of the energy we're consuming on the grid. So what does it mean? It means that at any given time during the day, depending where you are, they're going to tell you if your energy is generating a lot of CO2, a lot of green emission gas or not, based on where that energy was basically produced and how was it produced. So it's quite an interesting platform they have, and it's generating a ton of data. So what we put together is we're going to give you access during the entire weekend to the API of What Time, so you could extract the data that goes either in the past, or it could give you a forecast of where it's going to go in the future. So you could tell that, let's say take New York City, this neighborhood of New York City, let's take Brooklyn. So Brooklyn right now at this time is consuming that many kilowatt, and the source that energy is now coming right now from Quebec, let's say. So of course the green gas emission is pretty low, so the source is pretty clean, but suddenly they could shift to take the energy from Pennsylvania, which is generated on a coal plant, and then suddenly the same kilowatt is generating a lot of bad things. So depending on the day and the trend and what's going on, if you're basically having a big impact or less of an impact if you're saving that kilowatt at that given moment. And that is basically, and I'm going to share my screen, that is basically triggering an interesting discussion about the fact, and I just want to make sure that everybody see my screen. Please let me know if you don't see it, or somebody confirm you see it.
We see it.
All right, thank you. So it's really triggering the question about, okay, we want to save kilowatt. The question is, where do we want to save that kilowatt? And that, I think everybody clearly understand that a kilowatt save in Montreal versus a kilowatt save in New York is not the same impact. But there's another dimension, which is at what time are you saving that kilowatt? So depending on the time and the moment, you could basically source out where that kilowatt was manufactured or produced, if you want. And then the question is, how do you optimize that equation so you really want to have the maximum impact on the planet? And of course, you have limited capability. I think that's the core of the challenge here, is we're going to give you a capability. So we're going to give you these 3 type of building, and we're going to give you all of the information about all these 3 type of building do consume when they are operating, which is pretty much all the time. And now the question is, if you have these 3 type of building and you have a capacity of, in between 60 building at the time that you could do, and each building take 3 months to do, is where do you want to go do these building in North America? So do you want to concentrate yourself in Manhattan? Do you want to go all over the place? And to decide where, well, you're going to use that data coming from What Time to figure out what is the biggest impact. And keep in mind that this equation do change. So it's not a fixed situation. Each of these different areas are evolving through time. So maybe it was super dirty before, now it's getting better. So it's raising a lot of discussion about where should we put our effort in North America if we want to have the maximum impact with the given capacity to impact these buildings. And the tool we're using is AI. So AI come and optimize the building and lower the energy consumption of each of these 3 type of building. So the challenge is, with these information, how can you extract that information and figure out what is the best way to play with all that data, then visualize. So give us like a vision of the next 10 year of your plan of where should you go and to have the maximum impact on the CO2 emission reduction. And of course, I mean, that's going to be one of the key criteria in the evaluation of the challenge. So the mise en scène, so the sandbox. So as I said, you have a capacity of doing 60 to 80 building onboarding. So you cannot have more building being done at the same time. And it takes about 3 months to deploy the AI. Remember, you have to do the learning, the data cleanup, making sure your neural network is capable to do the job. And then you have to stabilize your neural network. And then you could go do another building. So that's your limited capacity. And you have 10 years. So do the maths. You have really no sales force constraint. So you could go wherever you want. If you want to concentrate in Detroit, go in Detroit. If you want to go in LA, go in LA. You're completely free to do that. The energy reduction of the profile of these buildings will give you is once the AI is fully trained and doing its thing, it's going to reduce it by 25%. So you could do the maths. That's an easy rule. And you have flexibility. And that's where it's starting to be a bit complicated, is if I'm reducing energy in one state, let's say Toronto, and that energy now is available to be sold to another region. So that flexibility is basically being shifted. So let's say we take the example of Montreal. If I'm saving energy in Montreal, I don't have a big impact on the CO2 emission, but that kilowatt is now available to be sold to New York. So I'm having an impact on New York. So that we're giving you that 10% capability to shift. What time I spoke about. There's a lot of other interesting information you could find in the What Time API, but I would say that the grid cleanliness is really the key one. So I spoke about the 3 types of building. There's high-rise residential that we see more and more on all over city. You see these huge condo tower. They're popping everywhere. There's also the office tower that you see in downtown core, and these large box retail, that's 50,000 square feet, which we see everywhere. Think of Costco, Walmart, these type of place. I mean, those big box retail, they do have high ceiling, they consume a lot of energy. So a kilowatt save is a kilowatt that you don't need to produce, but it could be shifted to a certain percentage. And all of the detailed information are in our AI handbook that it will be available. So I'm not going to go through that handbook, but you could see here, you got the pedigree of the building, you got all of the information, how do they consume. So you will have the detailed information for the building, and you're going to be able to play with that. So I just want to hear like 2 more slides. I mean, key question that you should think about. So how building energy flexibility can impact the building CO2 reduction? Well, that's the key of the challenge, right? So keep in mind that this is 24-hour a day. So most of the buildings, especially residential, they operate 24 a day. So it is something which keep consuming all the time. So if you lower that production, you're having automatically a big impact. So question here, is it better to focus on the location and just looking at the flat line, or start to look at the variability of the grids, meaning that depending on the time of the day, that kilowatt could be very dirty or could be super clean. So now you start to wonder, like, maybe I want to save at certain time of the day and not at others if I want to have a bigger impact on that CO2. So see how it could be suddenly very complicated. So just making sure by respecting the time and not taking too much time, we're just going to jump on some of these questions. And we are going to be available. So Vaskin, which is part of our team, will be checking in every morning and be available to answer question in case you have it Saturday, Sunday, and you want to pick his brain. He will probably give you a couple of tips too. So just want to do a quick stop on the criteria. So I think there's 3 very key important challenge here. If you subdivide the challenge in 3 pieces, how are you going to integrate the information? So what information you're going to use? How are you going to combine it with other information? That there's going to be an interesting criteria here to be evaluated into your result. Data visualization. How are you going to show that? So So I don't have to read 30 pages to understand what is your solution. So how are you going to show on a very nice visual way that maybe the map, it'd probably be map-based, right? What is your plan to deploy the AI in these buildings throughout North America to maximize that CO2 impact? And then the last one, of course, like, how many CO2 tons did you save at the end of the day during that 10-year? So that is the three criteria that we'll be evaluating on. So I'm available for question now or later. Feel free to contact us.
Thank you so much, Jean-Simon. I just want to open up the board. If anyone has any questions, please send them in the chat now. I can ask them on your behalf. Thank you so much for that presentation. Very interesting to see the innovation going on. And once again, if any questions come up later, we are monitoring the Slack board, so we can check there in the question channels as well. I don't see any questions. Oh, so one person is asking if they should use the BrainBox AI and how.
Yeah, so you're basically in this challenge, you're using the BrainBox engine virtually, of course. And that is what is giving you that 25% reduction on the building profile that was supplied. So you know, a little tip here, check your 3 type of building because they don't consume the same thing. So, you know, it's where do you position that building and which type of the 3 building you want to position, because the AI will save you 25% on all 3 types.
Lovely. Thank you so much.
Awesome. So thank you so much, Jean-Simon. We will go to our next challenge presentation, which is #challenge-super-resolution. And we have Bertrand Denis, who is a major co-organizer of this event, and also David Landry to speak about the challenge. And this is a Kaggle-style challenge, and the climate change approach is adaptation.
So you hear me?
Yes.
See my screen?
No, we can see you.
Okay, sharing my screen. Now it's gonna work.
Yeah, now it's visible.
All right. Okay, so I'm going to present our challenge proposal. I've teamed up with David Landry from the Centre de Recherche Informatique de Montréal. I'm an adjunct professor at the Center ESCAR from UQAM, but I'm also part of the organization. So you'll see me going around in each challenge channels on Slack and on Miro too. So I'm sure you've seen that kind of plot showing increase of temperature or other stuff like precipitation. In this example is the hottest day of the year in Ottawa. So those projections are used to address risk posed by climate changes and anticipated impacts. Like you see the B there. So just this is to make the link with the challenge Be Healthy. So these are used to see the impact on those kind of well, the environment, like here the bees, because then when there's the heat wave, they suffer a lot. So the source of information to do those kind of impact studies comes from climate model projections. So what are those climate models? Those climate models, mainly we're talking about the global climate models here, are complex computer programs representing the physical interactions of the Earth systems on the left. And they require very large computer resources to produce just one climate simulation, but we need to do a lot of them to be able to estimate the projection uncertainties. So on the right is just a cartoon of what is a climate model. Essentially, you put a grid on a globe and you compute for each cube the physical interactions. I mean, the equations, Newton equations, radiation, Planck's, and all that stuff, chemistry included. Okay, so this is very costly. So because it's costly, the resolution of the grid, so the level of details that we can afford, is it's not very, could be better, okay? Because it does not fit the needs for adaptation planning that are requires at the local scale. So what we need is a kind of a magnifier, as you see on the pictures. And there's two solutions. Well, in the climate science community, we call them the climate downscaling approaches. Mainly there's two. First one is the dynamical downscaling. It is simply to have a climate model, not over the globe, the entire globe, but just over a region. Could be North America in our case. And this is the kind of climate model that is developed at UQAM. It's called the Canadian Regional Climate Model. It's still expensive because you increase the resolution, even though you're in a smaller region, but it is expensive. So the other way is to do statistical downscaling. So it uses empirical relationships between historical large-scale atmospheric conditions and local climate characteristics. So it's not based on physical principles, Newton's law, the thermodynamics law, etc. So both approaches have pros and cons. And the advantage of the statistical downscaling approach is that it is computationally inexpensive comparing to running the original climate models. Okay, so our super resolution channel, and I will explain why we call it super resolution, falls in that statistical downscaling category. So, well, the idea is to downscale or to magnify the resolution. So on the left, it's a typical grid box from a global model. Okay, so it will give you an average over, let's say, 100 kilometer by 100 kilometer. But what you want is something at the very local scales, because it is at that scale that you will have useful information. Just going back. So what is, well, on the right, it's the same idea. You take a small piece of the of your region and you apply a process to get details, the downscale information. So just to give you an idea, on the left, you'll see a global climate simulation from a global model, which has somewhat lower resolution. Then on the right, which is a regional climate model. Okay, so you see the level of details much more better on the right. But again, those two are models running on supercomputer. Then came the super resolution, which is an active area in AI currently. So it's a class of techniques that enhance increased resolution of an image. So what you see here is on the right, that's the original, but we started, well, the researchers started from a blurred images and they applied different techniques to add information to the image. So there's already, since about 4 or 5 years, techniques that has been developed, they are becoming better and better. You can even online put your picture at low resolution and they will give you back your face with more details. Realistic details, but not necessarily good. Anyway, one warning is that we call it downscaling process, but in the AI, they call it upscaling. Okay, so for AI people, you'll see downscaling, but for you, it's upscaling, means upscaling, okay? So your challenge. So can recent AI techniques be used for climate downscaling? So you'll have 2 days to build your model, to train, to validate. And so ideally, because you have just 2 days, your model should be cheap also to train and run and should be accurate. Not too complicated. We don't want an ensemble of heterogeneous models or spaghetti code, stuff like that. So it has to be easy to maintain, even to operationalize, let's see, to do weather forecast with that. So simpler approach are often faster to test, tune, refine than other approaches, like if you use linear regressions, that's an extreme, and deep learning GANs. So here's some guidelines. The data set has been packaged in a way to ease their usage, thanks to David. The total size is 25 gigs, so it's not a spreadsheet, okay? But fortunately, David has prepared a tutorial. It's a Python notebook. So with that, you will have everything to access the data and do some manipulation, some selection of variables, and even some plotting. So you should start with that. And something that is special to weather and climate, or to the atmosphere, is it's just not a transpose from low resolution of temperature, because that's temperature we're looking at, from low to high, but you can take advantage of other weather parameters, like total cloud, sea surface temperature, total precipitation, stuff like that. Okay, so as a hint, climate models are not color TVs, okay? But they are closer to that than black and white TVs. I don't know if you understand, but I'm sure some of you, yes. Okay, so the challenge proposal expectation. So your submission should contain a short technical report. Should be accompanied with a proof of concept, so some code, hopefully a prototype that works, okay? And you should consider some things like, will it perform well in case of extreme events? Is your algorithm is good, but just in average, or can it handle extreme events, okay? Can it produce intense precipitation from a field without intense precipitation? Okay, so we'll look at the quality of the prototype, and do you come up with new ideas? Okay, that's very important for us. What else? So does first of all, you look at the temperature, and we should be able to say if it makes sense or not, okay? So we'll ask you also to provide some matrix of the performance of the accuracy. Okay, so basically, let's start with the root mean square error. Okay, so the challenge description, this is the talk, but can be found on DevPost and also on the Slack channel. And also, David will be around from time to time on Slack to ask questions, to answer questions, and myself too. But David is the AI guy, and I'm more the climate guy. Thank you.
All right, thank you so much, Bertrand. Do we have any questions?
So far, no questions yet, but if anyone wants to post that now in the question and answer chat board, be happy to ask the questions for you.
Awesome. And yeah, I also just wanted to mention that this challenge is also related to mitigation because it can make a difference with regard to prioritizing ways to reduce emission. So seems like maybe no questions still. Okay, so let's thank you very much, Bertrand, and thank you very much, David, for that presentation. We're going to go to our next challenge, which is #challenge remote communities. And this has two challenge types. the Open Challenge, as well as the Data Visualization Challenge. And the climate change approach is mitigation. So we are very lucky to have Ryan Kilpatrick. And also we have Aaron, and I'm sorry, I don't have your last name with me. I'll let you introduce yourself, my apologies. And also we're joined by Ricky Lee Watts. And both Aaron and Ricky Lee are from Indigenous Clean Energy. So thank you so much for presenting today.
All right. So good afternoon, everyone. As our managers mentioned here, my name is Erin Stewart, and I'm joined here with my colleague, Ricky Lee Watts. I am calling in from Haudenosaunee territory and Six Nations territory, also known as Hamilton. And I'm going to let my colleague, Ricky Lee, take us away in terms of introductions.
Perfect. Just plugging in my headphones here. And can you hear me?
Yep.
Perfect. Hello and good day, everyone. An absolute pleasure to be here with you. Thank you for the invitation, and really grateful for the opportunity to share and connect, offering a brief introduction of myself in my language. Uklama amitla, hupachas aksup, huchaklas aksup, nu chalnal at, his stakshitla suma as. So I share my name is Amitla, which means blessed one in Nuchonalth. I am Hupachas Nuchonalth upon my mother's side. My father's ancestry is a mystery. I am coming to you today from the West Coast, Vancouver Island and Nuchonalth territories, Port Alberni, BC. So we're in a moment in time looking at the kind of work we want to do in this moment through this hackathon in our communities, and looking at the world and the state of the world of where we currently are. What I want to do is share a little bit about cultural teaching that I've learned, as well as the opportunity that we have going forward here. From my late grandfather, he has always shared with me the importance of interconnectedness, about respect, and two Nuchonalth values. One is Hishak Ish Sawak, meaning we're all one and interconnected, whether we're looking at people globally in different communities around the world, no matter their walk of life and where they come from, the land, the environment, the plants, the trees, the animals, looking at the interconnectedness of our systems and how that works together. And respect no matter what backgrounds we may come from, respecting who they are, their strengths, their gifts, their ability to contribute. Looking at this and looking at where we are right now, faced with the global pandemic, the climate crisis, these circumstances only highlight and show the socioeconomic disparity existing. And we have a moment in our history to act now and think about what are some innovations and solutions we can bring forward to challenge and be the generation together that solves and handles these challenges we're presented with globally right now, with climate crisis, pandemic, and things like this. No matter our walk of life, this is something we all face globally. And looking upon this, we can be the generation that makes that change. And looking with where we're at right now, just want to make sure I touch on how, rather than ignoring that discrepancy, rather than ignoring those hardships, the abuse to our common home, the planet, we look to what we can do. We look to renewable resources, to clean energy efficient homes, and about how we can handle this challenge in front of us right now. So maybe let's jump on to the next slide. So with that in mind, I've recently joined the Indigenous Clean Energy team, and it's such a privilege and honor to do so. I was looking about my next walk in life of what I'd like to do, and joining this team, the meaningful work available, it really is such an amazing opportunity. So ICE, who are we? Indigenous Clean Energy Social Enterprise is an independent, Indigenous governed nonprofit organization. ICE works to advance Indigenous and broader sustainable prosperity by supporting First Nations, Métis, and Inuit clean energy participation in every region of Canada. in ICE, I've learned so much in my own energy literacy and looking about my own passions and skills and experiences, coming to a space where I can make that meaningful contribution. And the history and impact ICE has already brought forward on the next slide.
There we go.
There we go, perfect. As has already created, and the impact that has unfolded thus far is really incredibly notable. You can see the numbers here really signify the collaboration and working with Indigenous communities across the nation with 197 medium-large renewable energy projects. I believe medium-large is over 1 megawatt of work and of those numbers. And then looking at our bioenergy project, energy efficiency, large-scale transmission. And the biggest thing to note here is Indigenous communities are the largest asset fund holder and really one of the biggest players in driving that change for clean energy. Looking at all the players in the field of clean energy and driving that movement, I think about my own teachings and at other Indigenous communities and allies and people who have come forward to take that step forward. That's really respect to our interdependence, interconnectedness, and with these values and with people driving that passion and with innovative solutions and ideas and research backing that up has created enormous impact. And that's simply to say I'm so proud to be a part of ICE and the work that is being done. And this really is that innovation we're looking for to create the change for our futures, for our communities, for all of our communities globally. And I'm really excited that you're all here today looking at what you would like to do for the hackathon. And from here, I want to pass it over to my dear friend, colleague, and mentor, Aaron, who's going to share a bit more about this opportunity with you. So I'll pass it over to you, Aaron.
Great. Thank you, Ricky Lee. So I wanted to take a couple minutes just to go over a bit about ICE, and then I'll frame it in how this challenge is working, and then I'll turn it over to Ryan Kilpatrick. So in terms of our ICE programming, we're really focused on Indigenous clean energy capacity across the entire country. We host capacity buildings on community energy planning, community engagement, project development, everything soup to nuts in terms of business planning to project feasibility into construction, employment, and operations. And we do that through many different facets of engagement, whether that be online conferencing. We're just finishing up our annual conference that brought together over 600 people from across the country, our on-site intensives through the 2020 Catalyst program, our online network, which has over 1,200 members talking about it's free and open for anybody to attend around how to advance microgrids in diesel-dependent communities to community scale energy efficiency projects. So you can go to icenet.org to find out more. And also on a global stage as well, as Ricky Lee mentioned that there's 197 projects that have significant Indigenous leadership that are over 1 megawatt or larger. Indigenous communities are the largest single asset owner. That's more than municipalities, and it's right next to that of utilities or government-owned projects. And so, the community Indigenous leadership is so vast across this country, and we want to show that globally. And so we'll be going to COP26 and showing some of these examples on a global stage, as well as trying to get lessons learned from Indigenous communities across the country of how we can do things better here. And those are some of our programs. I know that many of the people chiming in and attending this hackathon, and thank you again for being here, are actually youth themselves. And when I say youth, I mean, between the ages of 18 and 30 is what I've been told. And we're actually starting a new program called Generation Power, which will focus on making sure Indigenous youth are represented in the energy sector by giving them internships and jobs and career opportunities, and also providing equity and diversity training to employers in the energy sector to better support those Indigenous youth. So this is some of the work that we're doing at ICE more broadly, and we've seen so much success with our programming. As Ricky Lee mentioned, we have representation from coast to coast to coast, and this actually doesn't even include this year's 2020 cohort. So we've got another 22 communities that we've worked with, mainly in the northern regions and remote regions as well. Just to show kind of where we're located and all the things that we're working on in terms of project development. But what I'm here to talk about is actually this project case that we are really interested in knowing more about. Last year, we brought together Indigenous communities, probably about 100, and we brought them to the CanMet, NRCan's CanMet labs, and we did a whole tour of all of the different research that was going on at CanMet. And one of the things that these community energy champions brought up was the need to have information that they could embed into their energy profiles. And they talked about the fact that that kind of information is not readily available for diesel dependent and remote communities. And they would like to, from their own community capacity, see more of this information available to them. And so that's why we bring this challenge to you, is to say, this is actually a very tangible need on the ground in Indigenous remote communities right now. And if you're able to work on this hackathon challenge, we would greatly appreciate the support. So I am actually heading up, in partnership with Natural Resources Canada, an initiative called the Indigenous Off Diesel Initiative. And what that program does is it supports 15 Indigenous remote communities from across the country to transition away from diesel over a 3-year period. And so each of these communities are actually being awarded $1.3 million to do capacity building, to do energy planning, to do project development, and training, and then ultimately develop projects that are reducing diesel in their communities. And so what I've shown you here is just kind of what we've gone through in terms of developing this program, from some of our pre-launch activities to training the champions on energy literacy through ICE. And now they're actually in the phase where they're developing their community energy plans. And with these community energy plans, my expertise is actually in energy planning. I wrote a book called the Arctic Community Energy Planning and Implementation Toolkit that was sanctioned for the Arctic Council for all of the circumpolar Arctic. And one of the biggest challenges with energy planning is that it's actually not community led. You usually have technical leaders from the South that are writing these reports from at their desk and kind of making recommendations for the community. And what the biggest challenge is with that is you end up with a report that becomes outdated very quickly. There's no community buy-in. And as a result, the recommendations that they're making actually don't get implemented. Further to that, there's actually not funding or financing regimes in order to implement those projects. And so with this challenge, what we're really looking at is creating more information to create those energy profiles for these communities. So like I said, this is directly applicable to what we're doing right now. And so what I'm showing here is just all of the different communities that we're working with through the Off Diesel initiative. So you can see, we have 3 Inuit representatives in Nunavut. We have 1 in Nunavik, which is also known as Northern Quebec. We have 1 in Nunatsiavut, which is in Northern Labrador, as well as 1 in Southern Labrador, Nunatukavut. We have a couple representatives in the South, but in remote diesel communities in Northern Ontario, 1 in Northern Saskatchewan, and then 3 remote communities in BC that are working on these initiatives. And so, the key part of this proposal, or of this challenge, is really looking at the fact that Indigenous communities, where most energy is spent, is there's actually 70% of their energy bills are on heat. And so we really want you to look at heat, and Ryan Kilpatrick's going to go in a little bit more detail about this case itself. But what I thought I might do was just tell you a little bit more about how this information is going to be used right away. So the first one is working with Kujimute Inc. And Kujimute Inc. is in the community of Kuujjuaq, which is in Nunavik, or also known as Northern Quebec. And what they are working on in this phase of their project right here on energy planning is a couple things just right now. This is in the course of the last 2 months. This is how busy these people are. Is they are reviewing a high-level, they're doing a high-level review of a 100 kilowatt rooftop solar PV proposal in terms of its cost. I don't know who that is. Anyway, we'll turn off their mic, I'm sure. We're looking at a high-level review of a 100 kilowatt solar project. Can somebody turn their mic off? Thank you. So we're doing, they're doing a high level performance of a 100 kilowatt rooftop solar project. They're going to be doing energy audits of all of their community buildings and 50% of their residential building stock. They're also looking at integrating electric vehicle charging stations in their community. And they will be actually doing that around their arena and their arena garage and also their community pool. They're also working on a horizontal geothermal heat pump system that will actually offset the heating, the swimming pool heating costs, and that is located directly across from the arena. And they're also working on some heat pump systems. So let me talk about this challenge in terms of the direct applicability. If we're looking at an energy profile and we're able to already see all of the community buildings that are there, look at what their energy needs are, and also what kind of residential stock they have in terms of multi-residential, single detached, is it social housing, is it owned by communities, what kind of arenas, how many do they have, is it ready for solar integration? This is information that communities can use. So this is a perfect example with Kujimu Inc. and how this work can be related. The second one is with Nitot Energy Limited, and Nitot is a Gwich'in-owned company located in the Northwest Territories. So Gwich'in communities are in the Northwest Territories, Yukon, and into Alaska. And what Nitot Energy is doing is they are looking at feasibility for both a biomass and a solar project, 1 megawatt solar project. They again are going to be doing energy audits of all of their community buildings and 50% of the residential homes. And they're also looking for the high level infrastructure needs to support pellet distribution in their northern environments. And so again, you know, Nitot is putting together energy profiles for all of the Gwich'in communities in the Beaufort Delta. And if they're able to access this information readily, they can put more of their dollars towards these kind of projects. And finally, I wanted to speak about Saku Investments. So Saku Investments Limited is an Inuit birthright company located all in the Kavalik region of Nunavut. And Saku Investments represents the interests of these communities that you see here of Baker Lake, Chesterfield Inlet, Rankin Inlet, Whales Cove, Arviat, but as well as, oh, I'm forgetting, but there's two other ones that are not connected to this transmission line here. And so what Saku is, it's going to come to it. One of them is Nauyat and the other one's Whales Cove. Oh no, Whales Cove's there. Nauyat and anyway, whatever. I can't think of it at the moment, but this transmission line that they're proposing will actually connect these 5 communities to the Manitoba electrical grid. And so those communities will actually be connected through here. And so what Saku is working on is with the other 2 communities of Nauyat and insert name that I'm forgetting at this time, they are looking at high-level comparisons for heat loads for their community buildings. They again are doing audits in all their community buildings and residential, and they're looking at the technology and financial aspects of their alternatives for heat loads. And they're also looking at the feasibility of this transmission line, but that's a way bigger project. So, I mean, I talk very fast. I know that I have a lot of information to share, but what I'm hoping to do here is just knowing that this project has real applicability right away for these communities. You heard Ricky Lee's opening remarks in terms of the importance of Indigenous worldview and values and making sure that we're having that Indigenous leadership. And so if you can do anything to support that and are coming together for that, we would be appreciative from our perspective. So without further ado, I will take some questions if there are any. I know I have 2 minutes, and then we will turn it over to Ryan to actually get into the case details.
Thank you so much, Erin and Ricky Lee. That was a wonderful presentation, and it's honestly so inspiring to hear the work that's being done and that you guys are doing. So thank you very much. I'm just checking over from our participants. We had A brief question about the internship you mentioned. This may be a bit technical, but they're wondering if someone who is a bit older than 30 would be eligible.
So we have a couple different forms of the internships itself will be for that age bracket of 18 to 30. We'll be working with Electricity Human Resources Council, Eco Canada, and Natural Resources Canada, which has that age requirements, their age requirements, not ours. However, a lot of the information that we'll be providing through Generation Power will be open source and available for anybody to use. So the internships themselves will be reserved for people of that age group, but the information is going to be shareable and accessible to others.
Wonderful. Okay, thank you so much. I'll be sure to pass that along, and I hope people do take up the opportunity to get involved with that. Just to everyone listening, this is your last chance. If you have any questions you'd like answered right away, please share them now in the Q&A box or in the chat. And if not, again, we will always pass along questions as they pop up.
Yeah, of course. Get in touch with us if you want to know more information. And yeah, be sure to check out our webinars and all the information on our website. Thank you.
Huge thanks for listening. Excited to see what you all do. Thank you.
Thank you. And now we're going to look to introduce Ryan and also talk a bit more about this challenge as things move along. So I will open up the board now for this introduction. Thank you.
Okay, perfect. Thanks very much. I'm going to share my screen here. Hopefully that will work. Hi everyone, bonjour à tous. I'm Ryan Kilpatrick. I'm a research engineer at Canada Energy Ottawa, a federal lab within Natural Resources Canada. And I just want to say thank you very much again to Rick Lee and Aaron for their inspiring words and for discussing all of the exciting work that's going on across many Indigenous communities across Canada. So in partnership with Indigenous Clean Energy, I'll be presenting a challenge today for your consideration related to remote community energy building stock. So Natural Resources Canada is one of several federal departments who are supporting the transition of remote and Indigenous communities from reliance on diesel-fueled power towards clean, renewable, and reliable energy by 2030. The Clean Energy for Rural and Remote Communities program, or CERC, is one of NRCan's funding programs for clean energy, and it currently includes 62 renewable energy projects and 85 capacity building projects across a wide number of communities, many of which are involved in the Indigenous Off-Diesel initiative that Aaron mentioned, or who are represented by energy champions within the ICE network. At the Canada Energy Ottawa Lab, we're currently examining and supporting transition efforts for communities by conducting analysis on potential options for communities, both for new forms of renewable energy and storage, but also for energy efficiency improvements in buildings, for example. So we have these various modeling efforts that are underway to determine how communities can transition away from diesel in the most cost-effective and reliable ways possible. But underpinning all of these efforts is the need for accurate information on community building stock. So in other words, the size, the age, the type, and other characteristics of all buildings in the community. And there are roughly 200 remote communities across Canada that rely on diesel fuel as their primary energy source for both heating and electricity. So here's the challenge in a nutshell that we'd like you to consider. Can we develop a feasible approach using AI and machine learning techniques to generate a complete characterization of building stock for every remote community in Canada? So when we talk about characterization of building stock, this would include identification of all the buildings in an area surrounding the centroid of the community, calculating the building footprint in meters squared, for each building in the community, classifying the buildings into archetypes such as single detached homes, multi-unit residential buildings, commercial buildings, industrial buildings, etc. Another valuable outcome of this work, which Aaron touched on, is identifying the potential for rooftop solar in community buildings. So this would just be, the generation of this type of database would just be one piece of the puzzle that we, in conjunction with other survey information and existing information, communication with representatives in the community, this would form part of an ongoing modeling effort to ultimately put this type of information in the hands of communities and people who can use it. So the challenge objectives are to prepare a methodology for achieving the desired outcomes using machine learning techniques. Or perhaps you've heard of the concept of machine learning canvas. This is what we're looking for. It's really a proof of concept to demonstrate that a given approach can be successful on a larger scale. And this could form the basis of a future project if we can develop some more detailed learning data sets, for example. This could be part of a future Kaggle-style competition. So I'll just leave you with a call to action. Can we harness modern AI machine learning techniques coupled with government and private sector investment, Indigenous knowledge, and community energy champions to support Canada's remote communities transition away from diesel fuel and toward a cleaner energy future? I believe we can, and we need your help. So thank you for considering this challenge, and I'm happy to answer any questions.
Thank you so much, Ryan. That was another wonderful presentation. And I really appreciate your call to action towards this incredible project. I hope people, and I'm sure people will, get very invested in coming up with some creative solutions here. I'm just going to give everyone a quick minute. If there are any questions you want to send in, please send them in now. And again, if you're sending them in on our YouTube live stream, there's a little bit of a delay, so we will most likely answer those questions via Slack. But anyone who's here on Zoom, please feel free to send your questions in.
I can mention also that I'm happy to check in with the teams on Saturday and Sunday to see how you're doing and offer any advice where I can.
Wonderful, thank you. I'm sure the teams would really appreciate that. So I don't see any questions coming in. I'm going to say another big thank you, Ryan, Ricky Lee, and Aaron, all of you. This was a wonderful presentation, and we really appreciate you taking the time to share it with us today.
Okay. Thanks so much, Shada. Appreciate the opportunity.
So now I'll just pass it back to Monika or Tim, if you would like to take over now.
Yes, absolutely. Thank you so much for those great insights. It's really important to learn about these communities and about the history of where all of this is coming from. So it's a true honor to have such great insights from all of you. Isn't that right, Tim?
Yeah, exactly. We're really lucky to have had all those amazing presentations, and I really can't wait to see what the outcomes are from all of the awesome participants. And actually, I did want to mention as well that participants are from all over the world. So many of them are actually not able to watch this live because of the time zone difference, and they'll be watching it later today or tomorrow, depending on what time zone they're in again. So that's another really cool thing about this, that everyone's kind of coming together to work on these from all over the world. And yeah, just about the last presentation again, really important that we listen to you and make sure that those communities that are most affected, and also those communities that really haven't had any impact in terms of creating the climate crisis to begin with, that they have a lot of the say in terms of how we actually address this climate crisis, and so they should really be empowered. So really grateful that we were able to have Ricky Lee and Aaron Stewart to talk about what they're doing with ice.
Absolutely. I need to find where do you find this on a keyboard to use those symbols? I wish that we could have a tutorial on that. I love, the authenticity of bringing this forward. So, guys.
J'aime vraiment l'authenticité et cette beauté de présenter.
So guys, those were the 9 challenges that you'll get to pick if you haven't picked them already. As mentioned, once again, if you have more questions, do not hesitate to go on the Slack channel related to each of those challenges. You can browse the challenges with the plus button on Slack, but also all the information will be on Miro. And if some of the speakers would like to share some of their presentations, we will make them available on the main stage on Miro. So we have actually, yeah, go ahead, Tim.
Oh yeah, sorry. I was just going to draw attention again to those who might be joining us later that if they did want to watch this presentation in French, as you heard, I think we got a little bit of a snippet of the audio coming through. They can click on Zoom. There's a little thing at the bottom right that says interpretation, and they can switch languages to French. So we're really lucky to have had Julie do translation earlier, and now we are very fortunate to have Violaine continue for the rest of the event.
Absolutely. Alors, les francophones, n'hésitez pas à utiliser l'option d'interprétation. So guys, that means that the first portion of tonight, we have went through it by introducing the 9 challenges. You have to stay tuned because it doesn't mean it's over. We have 4 great, really honorable speakers that will present really true insights coming up later at 5:30. So until then, we have a few little bits and elements we have for you guys for the next half hour until the first speaker. So I'll let Jason, our colleague, to give a little bit of an overview of our ice freezer concepts.
Thanks, Monika. Hey, by the way, like Tim and Monika, I mean, you guys are doing a fantastic job, and everybody else has been on here. I think it's just been going super great, and it's been working really well on the YouTube link. So just kudos to what you guys are doing. I just wanted to say that it's going super well.
Yeah, thanks to the team.
Yeah, amazing. So yeah, I'll talk to you a little bit about this, our ice freezer activity. Or we don't want to use icebreaker because we're doing a climate crisis and we don't want to break the ice. So we're calling it an ice freezer activity. So let me share my screen. Sorry, and I'll show you what this is all about. All right, so this is Miro. So if you haven't clicked on the link or had a chance to go to Miro yet, I would encourage you to do so and make sure you get your user ID. Follow the instructions that were sent to you by email. There's a few key points that are important in order to make your experience pretty smooth. So on this Miro board, you see is the main stage, and this is where all the key information you'll be to find. And you can already see there's little cursors moving around because there are people that are already on this board, and as you get on, you'll be able to see each other move. So what I'll focus here though on right now, sorry, is this ice freezer activity. And why we put this here is kind of give you guys an opportunity, one, to just a little exercise to get used to Miro, just kind of used to putting stickies and things like that, which will help you work the board. But also it'll give you a chance to get to know your other colleagues, the other people that you're going to be working with. So let me just show you why that is. So here, right in the middle of the ice freezer instructions. So I'd recommend you click on this link, and this will give you the first just high level of how to do these little activities. So what I will do though is kind of show you what would be in this video right now. So first of all, you would claim a square. So there's tons of squares all around here. You just take one of the squares as put your own, and you can put stuff in it according to this these activities. So here in the first one, it would say to create a colored shape and put it in. So these are the hair from the side. That's a sticky note. Here are the different shapes. You can take whatever shape you want. You grab a shape. I'm just putting it here, and you can drag this into whatever place you want, and you can make whatever size you want. And you can add text, and in there you would just put your name as an example. And you see like Christina has already done one here. There you go. We have like Aragon who's already in there, and he's giving it a go. So that's fantastic. The next one is grab a sticky note, and there's the sticky notes. So you can grab a sticky note, grab whatever color, you can throw it in your square as well. You can adjust the size, you can adjust the sizes of the font. And in there, you can put like your passion or your interest, whatever is your passion. It could be your work, maybe your work is passion, but whatever else is your passion, anything you like in that. Then the third one is you grab a card. So you can grab a card. That's from this one. And in there, you can write your Slack, just your name, email if you want, but probably a Slack is probably better. Just put your name in there so we know who you are. And then you can put an image. Here I put the image of my favorite city. That's Barcelona. I actually lived there for a little bit of time. And how you would do that is you go here into the Google image search, and you can search for images of whatever city is that you like, and you'll find images of that city. You can grab it, select it, and it'll upload that image, and then you can adjust the size and put it in. I added a little bit of text later. So I wrote it was Barcelona, because I figured maybe people wouldn't really know what city it is. So for example, Christina already did one. It was great. She added like a little shape around here. And I don't know what city this is, but it looks super beautiful, and I would love to go there. So maybe you could add the city. I didn't have this name down there, so that's why she probably didn't put it. We also have another person here. She was the first one to do it, or here, Yuri. So this is great too. This looks like New York, so it's New York. But when all these are done, this is it. You can have a chance. You can get a chance, browse all these squares, see who you're going to be working with, see what their passions are. Look the name. You can contact them on Slack or DM them. You can like, we're going to have these breakout rooms in Rally. You can go to Rally, maybe create a table in Rally, chit chat together. So I think it'd be a great way to learn about Miro and to get to know your colleagues. So I think that is about it. And maybe I'll just show you, once you've grabbed your team and grabbed your colleagues, and this will help you get to know people. Look, I see all the people going there right now. It's super cool. The challenge boards are over here, just as a reminder. So for example, if you wanted to choose the sea ice challenge and you're ready to go there, you click on that link, and it's going to bring you to the collaboration board. Now this is where you can do all your work. You can choose a spot here and get your team name. And in here, oh, cool, got some people in here too. And in here, you can put your team name, add it over there. But everything you learned in that icebreaker activity, the stickies, etc., this is like your own space. You can add them here. You can work together. You can add arrows and lines and draw stuff and frames and really get super creative in here. And I think it's going to be a great space that you'll be able to work together. So I really think this is a fantastic collaboration tool. You might even bring this back to your own workplace if you like it. So I think we've been using it, and I think it's fantastic. I think that's all I had, Monika.
That's great, Jason. So when can we do icebreakers this weekend? Will this be the only time?
No, you can, if people want to go in, I mean, we're doing a presentation now, and I know there's a lot of information being presented. So, I mean, if you have the time, or if you want to do it simultaneously, or I mean, whatever you want, but anyone can go in here at any time and complete this ice freezer activity. Just whenever you have the moment, whether it's after the presentations or if you want to do it during, if you can concentrate on both, go ahead, be my guest. Yeah, so I'd love to see all these squares get filled up, and I love looking at them too and seeing what people have put in there.
Yeah, it makes me feel like we're in a beehive and there's all these bees buzzing around. So I love it. And those are the blocks of ice that everyone will build up to make sure the water doesn't melt a bit.
I love here, Carolyn. She claimed her little spot right here. She's like, okay, don't take that spot. I'm gonna put stuff in there.
Smart, I love
Beautiful.
it.
Yeah.
And people are asking how, I think we still have questions from the crowd or people watching. Where can they get the link to Miro, to Slack? So where should they find this if they haven't already?
Well, it should be in the emails. I mean, an email was sent to everybody with detailed instructions. I know that Tim sent them out last night, so you should have it. Check your spam folders or something just in case, maybe it's in there. If for whatever reason you don't have it on the Slack channels, well, I don't know if people have, yeah, because one of the things to get to the Slack channel, I guess, right? But on the Slack, there's a help section for Miro and for a dev post. So we can, for sure, you can highlight it there and we can make sure to get you the password or get you the information to have it. How do people get to Slack? I mean, they're on this call. They must know how to get to this conference. So,
well, I guess the people who are on the Zoom call includes both attendees and participants. So the participants were sent the email which had the links to Miro as well as other information, and then we also sent out a Slack invite to participants as well. So I would urge everyone, definitely check your junk email folders, your spam folders, see if anything went in there. If not, reach out to us. We might not be able to get to you until later this evening, given the live stream. But I did verify a couple of times earlier today that everyone was sent, everyone who was kind of invited to participate if they applied, and that they did get those emails and those invites. So there could be some potentially a technical issue, but I would just urge to check on your end first to see if there's anything.
Yeah, we had a couple happen already, but we've been pretty quick, actually. Like, I know Tim's been in the conference, but we grabbed the information from Tim and we've been actively sending it out to make sure that everybody gets on as quick as possible. So yeah, let us know. We're here for you. We're here to help out. Awesome.
I love, look, there's more bees buzzing around as we're talking. So it's really great. Like to see.
It's great.
That's it. Like we've been working and innovating, Jason, thank you so much, and team working so hard, putting this together, creating a virtual world for you guys to feel as if you are in a room and you are interacting with people that could be on the other side of the planet for all we know. And it's nice to see it finally come to life or being used. So great work there, and looking forward to you guys being creative in there.
Yeah.
Kind of a funny thing, because when we do in-person hackathons, you almost just kind of assume things will go a certain way and you don't necessarily need to put as much thought into it. And in this case, because it's virtual, then you really need to create this environment from scratch. So really kudos to Jason, Monika, and the MTL Green for playing a major role in getting this done, because I think it's really going to add a lot of value to the participants throughout the weekend. There's a lot of structure, a lot of support, places to go if you need some more information or need help. And that combined with the mentors and the facilitators, I think it's going to be really awesome.
Yeah, I agree with you, for sure.
Yeah, really great. Thank you.
Thank you for the accolades.
So yeah, so guys, stay tuned, because there'll be more ice freezers opportunities through the weekend. So we will be posting them in the announcements, so you guys can take a break and have fun, get to meet together. So definitely won't be the last time you'll hear from the ice freezer activity.
Yeah.
Thank you, Jason.
My pleasure.
All right, so maybe I'll give a few words before our first keynote speaker comes up. I'd like to explain a little bit more to you all how the team formation will be happening at the end of the evening tonight. So I'll share my screen here for all of you to see how this looks. So if some of you haven't went in the Slack channel already, there is a Slack channel called Team Up. Under Team Up, you'll see already our colleague Paul that posted a link to what we call Rally. We mentioned it a little bit earlier. Rally, it sort of simulates you're at the bar, at the restaurant, and you can sit in different tables and you can meet and greet and meet actually and discuss with the participants that will be at the hackathon. So once we get there, I'll just show you guys how to use it here quickly so you can already get prepared for when we get there. But if you already want to take a look, we see Paul here is in the help desk, and I'll explain to you guys how this is structured. So essentially, as you all know, we have 5 challenge approaches, 3 challenge types that have a different climate approach, but essentially we have 9 challenges. So those 9 challenges were divided in 4 rooms based on the most major challenge type. So for example, we see there's a room called Kaggle Challenges. In here, you'll find sea ice, wind energy, and super resolution. So if you already know that you're interested in Kaggle style and that type of challenge, one of those 3, you can join this room. I'll show you guys how it looks like once you join it. There is also the data visualization challenges. So we know some of them have multiple options, but here we have the 2 challenges that mainly address this. We have reducing CO2 and smart buildings. So if you are interested in those, that will be the room you can go in. If you are interested in the projected impact, so really analyzing the impacts of climate change, the 2 main challenges here are Be Healthy and Sewage Overflow. And finally, we combined here in a 4th room, the AI Art Challenge, along with Remote Communities, that is an open challenge. So in here, you can join and meet people that are also interested in there. If ever you're not sure how to find a team, you don't know where to look, there's always gonna be someone from our team in the help desk. So you can definitely join the room, and we can see here that Paul is in there. Paul, put your pants if you're not there already. So actually it's telling me obviously that my mic is blocked because I'm using it here for you guys. But once you join the room, you'll have the option to split in multiple tables. So I see here there's already 2 people, and later at 8 p.m., that's when we encourage all of you to be there if you haven't chosen a team yet, and we'll allow you to basically meet and greet and form your teams, seal the deal with your teammates. And we recommend that teams are between 2 to 4 participants. Obviously, you can go 5 people, there's no problem, but we don't want super large groups just to make the virtual experience more adequate and the team amount of people more balanced. Once you are in a room, you are able to change and switch rooms. So let's say you are not sure yet and you're interested in multiple of them, you'll have a menu where you can switch from one room to another. And within each room, you'll have the ability to join different tables. So you can have multiple conversations and switch over. So we'll have a little short demo later with our members to show you guys how to proceed here. So that will be our team forming process. And from there, once you do create a team, you'll be able to go in Miro, choose which board will be the one that is associated to your challenge. And from there, you can put whatever team name that you want. And with the search option in Miro, we'll be able to find you, and both facilitators, mentors, and whoever needs to find you will be able to find you from team name. So we'll give more details a little bit later, but that essentially you guys will have the chance to do this. All right, so we have a very great speaker coming up at 5:30. So I recommend that we take a 10-minute break for some of you that want to grab a quick dinner, because definitely things are gonna go fast and there'll be a lot of interesting content from there.
Awesome. So in these 10 minutes, will we just chat?
So 10 minutes, well, we can show the schedule. And I guess if some of you want to grab a bite, including, I guess myself and Tim too will grab a quick snack. But yeah, we can chit chat here and there at the same time.
Okay, great. So see everyone back in 10 minutes.
All right, see you in 10. Welcome back, everybody. Hope you grabbed a little snack and your popcorn for the best part of the show. So welcome, everyone, to the second segment of our evening together. And it's about our keynote speakers. It is an honor to introduce tonight with us Alain Bourque, who is Executive Director of Ouranos. Ouranos is the innovation cluster on regional climatology and adaptation to climate change. Alain has also a master's in atmospheric science from the Université du Québec à Montréal, and during his career, he has completed many regional, national, and international scientific summaries, and he contributes regularly to media stories and policy discussions about climate change and adaptation. It is an honor to have with us tonight Alain Bourque. Welcome, Alain. Just make sure to unmute yourself. Excellent.
Sorry about that. It had to happen. Thanks for the introduction. Thanks for the invitation and the opportunity to present. I guess I will have to share my screen at this point, right?
Yeah, you can go ahead.
Okay. So you should see the cover, the first slide of my presentation right now, right?
Yes.
Okay, thanks. So yeah, fantastic for the invitation. So my name is Alain Bourque, as was said, really dedicated to climate change science in the context of adapting to unavoidable changes. So my presentation is going to be on my first objective is really, I guess, to give you kind of a key message is that to fight climate change, we need to both reduce greenhouse gases, but also, unfortunately, to adapt to unavoidable changes, as you will see. I have modified my typical presentation that I make on this subject, and I tried to make a special emphasis on the importance of data in order to arrive to support decision-making in both reduction of greenhouse gases and especially on adaptation to climate change, because it is the main mandate of Ouranos to develop applied research project on adaptation. So actually, as I was saying, well, yeah, that's right. So a brief description of Ouranos. So Ouranos is kind of a boundary organization that is supported and funded by various members. You have all of the logos there that I won't enumerate, but provincial governments, federal governments, municipal governments, some private sector, energy companies, mostly focused in Quebec, although we are working with Manitoba Hydro, Ontario Power Generation, and we are doing science and adaptation science at the regional scale because many of the impacts of climate change are happening at the regional scale, and that's the right scale in order to deal with the problem. So we do have a critical mass of experts, but we work always in network with other universities trying to connect research and users on the grounds. That's why we do have municipalities, for example, that are members of Ouranos in order to develop a very targeted application. And so we are kind of playing a leadership role in the co-development and co-production of applied and multidisciplinary climate change science in order to support adaptation decision-making. And here you have a nice diagram that it shows the challenge of working in a multidisciplinary environment in order to connect climate to hydrology, to biophysical impacts, to socio-economic vulnerabilities, and at the end of the day, to end up with decisions that integrate all of those factors. So just to give you quick examples of the type of work that is done, working with Université du Québec à Montréal and McGill University, for example, on regional climate models and the use of regional climate models, which produce a lot of relevant data in order to adapt to the upcoming climate that is heading our way. Working with Environment Canada on a website to provide climate services, climate databanks in order to help decision makers to use climate data and plan with the evolution of climate. Working again with UQAM and other land use planners on urban e-islands and to better assess the risks related with increasing heat waves in the future. And finally, last example is a major cost-benefit analysis project that we did dealing with coastal erosion on coastal zones, and because of wave action, disappearing ice cover because of warmer temperature. And this is an example near Percé, where the community has actually used project results, data analysis, to completely rethink their coastal zone and to make it more robust and resilient to sea level rise and storminess. So my presentation will, again, as you will see, regularly appeal to data visualization, data interpretation, data analysis, to illustrate, climate change and the implication at the regional scales to support adaptation decision making. So here is just a very quick example. Well, a few maps to illustrate, that the climate is warming. I could show you probably thousands of maps with various indicators showing that the climate is warming. I like this one because it's illustrating each of the last full 4 decades. We will very soon add the 5th decade with the 2010s that are completing as we speak. So we see that clearly the 70s had a more, a stable climate with some region of the world that were cooling, some region of the world that were warming. But at the end of the day, the climate on a global scale was pretty stable. But then going to the 80s and then increasingly to the 90s, we have been systematically seeing warmer and warmer temperature as time goes along. But you also notice that climate warming is not happening at the same rate everywhere, and that's normal because we do have climate change that is happening at the same time as natural climate variability is happening, as it always did and as it will also continue to do so. The only thing though is that, starting in the 2000s, the warming signal really became quite generalized to the entire planet, especially in the Arctic region, as you may suspect. And of course, it is expected that the 2010s is going to be, warming trends for most of the region of the world, and this will continue. And to illustrate this, before I illustrate the future climate that is expected with respect to one indicator, temperature, just want to highlight, the summary of the IPCC analysis that shows that the warming is increasing. So each of the latest intergovernmental panel on climate change scientific report, it's kind of the international body on climate change analysis, analyzing the situation. As you have seen, the number have been increasing, and now we have reached the 1 to 1.1 threshold. And as you may know, according to the Paris Agreement, we would want to limit the warming world to a maximum 1.5 or maybe 2 degrees Celsius warming at the maximum in order to avoid the more catastrophic type of climate changes that would happen if we continue to emit greenhouse gases. So my next slide is going to be an animation, which is again illustrating the role of climate models, climate simulators in better understanding what's happening and what will happen with the climate. So the animation is going to be go quite quick. So we're starting in the 70s, and you see that the temperature are pretty normal at the time. And then as time goes along, you see that the warming trends that were actually observed over the last few decades are well simulated. And we can, of course, use those tools to anticipate what's going to happen with the future, depending on which greenhouse gas scenario track we are heading for the future. So those tools are very useful to make experiments and to generate tons of data to do risk analysis, for example, at local, regional, or even national scale, in order to fully assess the potential impacts of climate change. So my next slide is basically to say that as translating those planetary trends to national portrait or national pictures, basically saying that Canada is behaving more or less as expected with respect to the evolution of various climatic variables. So you see the trends here at various stations in Canada, the trends in temperatures, which are obviously increasing, the trends in precipitation, which is also increasing because of a warmer world the atmosphere can capture more water moisture, which in turn activates the water cycle and generate more precipitation. On the snow side, though, during the winter, most of southern Canada has witnessed a decrease in snow cover, while the northern portion of Canada has witnessed increases in snow cover. And of course, the Arctic ice cover extent has been decreasing, and there's even some question of it completely disappearing in the upcoming decades. Again, with respect to information and data, there's an increasing amount of websites that provide information, data, graphs, trends that I invite you to go and consult. So this is the general picture for Canada, and there's a dedicated website that is available at this address that provide you a very nice overview. It was published last year, 2 years ago, of the trends with respect to climate in Canada. Now, I want to come back at the regional scale, though, because many of the impacts of those evolving climate parameters are translating into regional impacts. And most people are actually quite worried about the regional impacts, the impacts that affect their own neighborhood. And just to illustrate what's really happening and what will happen, let's say in Montreal, for example, from where I'm presenting at this point. So here in gray, you have the historical evolution of temperature for southern Quebec. And in red, you have the expected evolution of temperature under greenhouse gas scenarios with very little, let's say, control or decrease of greenhouse gas concentration in the atmosphere. And in blue, it's a scenario where we are successful in reducing the emission of greenhouse gases to the point where, at the end of the century, we actually go down to net zero emission, and we're able to stabilize the climate. Now, so what's happening with climate change really is happening in 4 acts. So historically speaking, there was no climate change, and natural variability, as I was saying before, was really controlling the variation of weather and the impacts that we could witness from the weather and from climate. Now we've gone through a few decades where now we have seen the emergence of a climate change signal because of the huge amount of greenhouse gases that has been added to the atmosphere. But it took time to get really more clearly the signal that climate change is confirmed, is really happening. And now this phase has happened with a warming temperature of about 1 degree Celsius. Now, what's upcoming is actually a little bit troubling because it does indicate that there is a significant challenge ahead of us. And so we're heading in this new phase, this new act of climate change, which is the 3rd act, which is the recognition that there is a certain amount of changes that are now unavoidable because of the amount of greenhouse gases that we have already added to the atmosphere. So if you look closely at this data, you're actually seeing that even though we would be very successful in reducing greenhouse gases and following the blue lines, the blue evolution of temperature, and being able to stabilize the climate within the next few decades, one noticed that there's actually very little difference in the evolution of the climate up to 2040. So the next 2 decades are going to involve impacts on the natural environment, on built infrastructure, on the frequency of extreme events, even though we are successful in reducing greenhouse gases. And of course, this highlights the importance of reducing greenhouse gases in order to avoid significant changes in the climate. So for example, for Montreal, this means average temperature of 6 to 8 degrees Celsius warmer than historically observed. So it's really very crucial to be able to reduce greenhouse gases as quickly as possible in order to avoid those changes that will be mostly happening after 2050 if we don't do anything. And we need to act now in order to avoid those 6 to 8 degrees Celsius scenario. There's also the recognition, unfortunately, that we will have to adapt to a warmer world. So in the range of 3 to 4 degrees Celsius in the Montreal area. And I highlight this because really when we talk about the fight against climate change or an integrated strategy to deal with climate change, you really have to think about both. You need to avoid those scenarios and reduce greenhouse gases, but you also have to modify the way you build infrastructure, the way you plan the use of land in front of rivers, for example, that are going to be impacted and generate more flooding in the future. And so integrated strategy to deal with climate change is really about dealing with the two aspects, reduction and adaptation to climate change. Now here I have a slide that's, again, very regional in nature. It's a province of Quebec. And I'm just showing pictures of impacts that were observed over the last decade that are really very coherent with a changing climate. And I say this because a lot of the science that needs to be done and the data analysis has, of course, to be grounded with what's happening on the ground, with the impacts and with the need of people, communities, engineers, et cetera, et cetera. So, you know, the impacts are going to be quite different depending on the context. So for Arctic Quebec, for example, there's going to be impacts on the lifestyle of Inuit people living, being quite used with the presence of lots of snow and ice cover and et cetera. Permafrost is going to increasingly melt, and it's going to generate issues with respect to land use and infrastructure. For coastal Quebec, it's going to, we very often talk about sea level rise and Holland and Bangladesh, but it's also happening all over the world. Any communities that is living in front of a coast is going to be impacted and is currently impacted by climate change. As areas where there's large natural resources are going to be influenced, forests, water cycle, etc. And of course, the more highly densely populated area of southern Quebec, for example, like urban areas, big cities, which rely a lot on energy, on infrastructure, on healthcare and things like that, are also quite increasingly impacted by those evolution in the climatic parameters. Same thing for rural areas and suburban areas, which are connected to climate. So I could make presentations for 30 minutes for each of those files. So obviously that's not what I'm going to do, but I just wanted to provide you kind of an overview of all of the, quite impressive variety of impacts and needs to make connection between climate and impacts in order to develop solutions. Completely frozen. Whoops. Hello?
Yeah, we have you back, Ellie. Sorry about that.
Okay, so can you see my screen right now?
Yes, we can.
Yes.
Okay. Okay, so very quickly to continue. So where to find climate information? I didn't want to add additional graphics for temperature, precipitation, frequency of extreme event, etc., but just maybe to rapidly summarize the fact that there's increasingly a huge amount of data that are available out there in order for people to make connection between data banks. And then in Canada, for example, there's been significant effort to structure the climate data information. And you have this very nice website, climatedata.ca, that can produce maps for a variety of indicators. And for us at the regional scale, we do the same thing at Ouranos with providing climate information, climate scenarios that fit with the administrative split of the province in order to make connection with provincial ministries, with municipalities. So there is a challenge there to ensure that the information is compatible with the tools that are used by some of the people that are developing policies and the people that are doing design of infrastructure, et cetera, and doing some some various type of planning. Other type of products that are available, very interesting, Climate Atlas of Canada that is produced out of Winnipeg and people in the Canadian prairies. What's very nice about this Climate Atlas is that you have connection with videos of people that are interviewed and that describe and even film the type of impacts that they are witnessing, you know, in a very nice virtual and technical environment that is very, you know, increasingly nice to use. And so you have also the Pacific Climate Impacts Consortium down the west, who's doing, you know, various other type of work valid for the Pacific Northwest. And maybe I want to highlight the fact that number 6, the last one, some international data banks that are available gathering all of the data of global climate models, or again, regional scale climate model, which have a higher resolution of data. And increasingly, this data is being used by a variety of crowds in order to make their you know, analysis, their impacts analysis for their specific subject, and to ensure that they, I guess, become more familiarized with this type of data and use them for to answer their needs. Because, you know, using climate data, there's lots of options, but it's actually quite complicated, and you do need to develop also the capacity in order to analyze this data. And just to illustrate some of the methodologies that exist in order to transform climate science into relevant climate services for different use. Here you have an illustration of the evolution of temperature for Montreal given by most of the climate models. So each line is a different climate model. So obviously we don't know exactly which one is right. There's some uncertainties, etc. But there's a way to use this information to make climate risk assessment and to assess the risks rather than the impacts, because you do have, at the end of the day, to manage the risk in an uncertain world, considering the, you know, the uncertainty associated with the evolution of climate. So here you have, you know, different methodologies in order to kind of translate this huge amount of data into more simpler things that can be used by people that are not, you know, data whiz kids or things like that. And I'd like to emphasize maybe the last one, the one on spatial analogs, which is very popular, for example, with farmers. So here the map is showing where is currently the climate that Montreal, or, you know, the rural areas south of Montreal, where is currently the climate that they will witness in 2050. So they want to see how farmers in those other regions, so in this case, it's, you know, it's Indiana, Ohio, Pennsylvania. And then so through this project, we were able to connect farmers from the Montérégie region south of Montreal with farmers from the US in order to try to make connection and understand what are the upcoming risks related with doing agriculture in a different climate. And that's, I mean, that's one way that you use data to make spatial analog and to help people to actually understand what type of risks there are in the future. And so this was just a quick example, which is basically being reproduced in all kinds of atlases or all kinds of product. And so here you have an example here where there's we have developed with people in the water sector hydroclimatic atlases that are, of course, transforming climate information into hydrological information in order to better connect with people that are much more accustomed to water data than to weather and climate data. Similarly, as I was saying before, with the agricultural community, you know, using the data and helping them to assess their risks and impacts. And for the agricultural community, for example, there's been many projects that have been done using the Atlas that shows, for example, for wine, there could actually be some opportunities over southern Quebec because of climate change, while for other type of growing season, of course, the impacts are negatives, or there are increasing risk with respect to water, you know, scarce water resources, etc., etc. So again, on a few, maybe a bit more detail example and illustration of impact. So here, one project only on the impacts on biodiversity, which is using a methodology of the optimal climate niche approach. So this is an example with a researcher from the Université du Québec à Rimouski, Dominique Berthaud, who led a large partnership team to identify what is the past optimal climate niche for the red cardinal, for example, and what's the expected evolution because of the evolution of the climatic envelopes under a changing climate. Did the same thing for trees. What's the optimal climate niche for white oak? And to illustrate the evolution, the likely evolution of those type of species. Again, government can take this information, this data analysis, to better plan conservation areas to ensure that some of the more vulnerable species are going to be maybe saved because even though climate change is happening, and in order to allow for them to move into corridors instead of disappearing because of human pressure, for example. So another example is, and it makes the link with the evolution of natural environment, the connection between climate, the white-footed mouse, and the evolution of Lyme disease. So there is a connection there, and it was proven with the data analysis. And since then, actually, actually a bit before, a bit after the study, the number of Lyme disease cases started to rise in Quebec exactly as the studies and the correlation between data was illustrating. Here, similar example with respect to heat waves, where you can make connection with climate data, land use planning, and where people have health problems because of a climate or because of heat waves that are generating very difficult conditions to live. Yes.
Hi, we just wanted to save a couple minutes at the end of the presentation to ask the attendees if they had any questions. So if you don't mind, I'm just going to cut in now. Thank you so much for this fantastic presentation. It gave a really good comprehensive overview of data and its role in, particularly, I enjoyed your emphasis on the importance of being able to communicate climate crisis data in a way that would be well received. Our attendees have sent in a couple questions. So the first one I have here is, do you believe that there is a specific industry that should be prioritized when we focus on the adaptation or the mitigation strategies for climate change?
I mean, that's a difficult question because historically speaking, we have been adapting to climate variability in parallel. I mean, the agriculture sector has been adapting to climate. The energy sector has been adapting to climate. The engineering community has been conceiving and designing infrastructure with climate. So I think it is possible to advance in parallel in all of those fields. And there is a confirmation of that because we have done that in the past. It's clear that everything that has to do with infrastructure is probably kind of a key component because we depend so much on infrastructure these days. But again, as we see, public health is also a significant issue, and land use planning. We see, for example, in Quebec over the last flooding of 2017 and 2019, we have seen how our risky land use development that we have used over the last 40 to 50 years have led us into a very vulnerable situation when major floodings are happening.
Definitely. Thank you so much. That really provides a unique, very well-researched perspective into the changes that we need to begin analyzing. And hopefully over this weekend, some of our participants and our teams will be able to come up with some new collaborative and innovative strategies to mitigate these problems.
Yeah, hope
so. Yes, thank you once again for your presentation. I hope so as well. I'm just going to pass things over now to Timothy and Monica, and I believe they'll be introducing our next speaker now. So thank you again.
Thanks.
Thank you so much, Alain. Merci énormément. It's so insightful. We see the power of using AI to really predict and follow the impacts on all these issues that are pertinent to everybody. So thank you again for this amazing overview, Alain. It was an honor to have you. So let's look at our next keynote speaker. Without further ado, I'd like to introduce Dr. David Rolnick, who is a co-founder and chair of Climate Change AI. And maybe we can share on the screen his poster. And he also serves as a scientific co-director of sustainability in the digital age. So Dr. Rolnick is also an assistant professor at the School of Computer Science at McGill University and also at the MILA, Quebec AI Institute, which brings over 500 researchers to research machine learning based in Montreal. Dr. Rolnick is also has a past working at Google and DeepMind, and he is also the lead author of Tackling Climate Change with Machine Learning. So it is a true honor to have you, David. And without further ado, we'd love to hear some words from you tonight. Welcome.
Thank you so much for having me. That's a nice test putting me through having to look at a large picture of my own face. It's always challenging for any of us, I'm sure. So I'm just going to share my screen. Hope you'll be able to see it in a moment. There, can you see my screen?
Yes.
Excellent. Okay. Well, I'll be talking about tackling climate change with machine learning, the overall space of how machine learning and AI fit into climate change mitigation and adaptation strategies. I want to start out with a little background on climate change, though after Alain's fantastic talk there, I don't know how much background really needs to be provided. Climate change is obviously a huge and increasing problem with increasingly severe effects that we're seeing in lots of different ways. Some of the effects of climate change are storms, which are both more frequent and more severe as a result of climate change. Flooding, which is happening more and more frequently. That comes from there are several different reasons for that. And I would just like really briefly go into that because I think it's a lot of misunderstanding. So flooding as a result of climate change comes because of storms. So storms can lead to a lot of water, especially inland. There can be a lot of rainfall. And as storms become more powerful and sort of weather just gets messed up in lots of different ways, we can get more flooding. Storms can also lead to storm surges if you're near the coast. So that can lead to more rain and sort of sea being pushed ashore. Flooding can also be a result of sea level rise. Now, sea level rise is itself complicated. People tend to think of sea level rise as a result of climate change being because ice is melting and snow is melting everywhere around the world, and that is true. Greenland and Antarctica are melting far faster than they were before. And the balance of ice is shifting. There's a lot of ice that will no longer be around on Earth. And that is leading to sea level rise. But actually, a lot of sea level rise is also because of the oceans getting warmer. So the ocean has absorbed about 90% of the heat that has been a result of climate change. So climate change, the climate is getting overall warmer, and that has meant that everything gets warmer, but water actually absorbs a ton of heat. And so a lot of that heat is in the ocean, and the ocean, like anything else, when it gets warmer, gets a bit bigger. And so that is actually the expansion of the ocean plus melting ice is what leads to rising sea levels. Okay, extreme heat, that's sort of what we think of with climate change. Extreme heat gets more frequent, and this can mean that in various places it's actually sort of untenable to live there. A lot of the Middle East is going to be unlivable according to many predictions, by the end of the century. Droughts, that can lead to loss of agricultural productivity, famines, and many other things. Droughts are a result of both increased heat and also just changing rainfall patterns, because climate is like this really big, complicated system, and climate change is also like lots of different kinds of changes. So like some places having different kinds of temperature changes than others, some places having different precipitation changes as a result of changing weather patterns, changing ocean current patterns, lots of different things. Fires are something that people think about a lot with regard to climate change. That is a super complicated issue. There are different ways that fires are related to climate change. The first kind is fires that are just not supposed to happen normally, like in Siberia, where there shouldn't normally be fires really, but they've been happening because of climate change. And that's really, really bad. There are fires that are happening in places like California, which are sort of a result of climate change. They would normally be happening, but they wouldn't be happening quite as much. They're happening more because the forests are really dry, it's really warm, and there have been things like pine beetles, which are also a result of climate change, actually. These pests have, because climate change has made things warmer, they've expanded their ranges, killed a lot of trees, and now those trees are burning. But California fires are a little bit more complicated because it is a place that would normally burn. Anyway, sorry, just like going into these things are really nuanced. Overall, fires are getting more common. Want to say the third class of fires, the Amazon rainforest, is not a result of climate change at all. It's because people are literally setting the Amazon on fire. They're cutting it down and trying to burn away the dead trees that they have created. So any fires overall being made more frequent as a result of climate change, but it's complicated. Some places just a result of climate change, some places made more frequent by climate change, and some places not a result of climate change, though if you burn the Amazon, that is a terrible thing for contributing to climate change because the Amazon is sequestering a lot of carbon from the atmosphere. Anyway, complicated. Climate change has all of these effects. It has uneven impacts, different places around the world. It affects differently, and really importantly, the parts of the world that are hit hardest by climate change are often the places that are most disadvantaged already. So climate change, like any other serious catastrophe, perpetuates existing inequities and exacerbates them. There are feedbacks. So climate change as a whole is caused by pumping greenhouse gases into the atmosphere. Those greenhouse gases include carbon dioxide, which is the main one, but also methane and nitrous oxide and a bunch of others. These are all greenhouse gases which are being produced by people. So we have severely increased the concentrations of these greenhouse gases in the atmosphere. There are also feedbacks. So what a feedback is when you start something in motion, it is accelerating, actually. So some of these feedbacks are, if you melt ice, the Earth reflects less light back into space, and that causes what's called reduced albedo. So albedo is like how reflective the Earth is, and if you remove the white part of the Earth, the ice, then the Earth suddenly starts absorbing even more light, and so it starts heating even faster. So this is a feedback. It feeds on itself. Also called a vicious cycle. Another one is permafrost melting. So in the north of Canada and Russia, especially, there's permafrost, which is sort of the ground being frozen, or at least it should be frozen. Now it's melting because of climate change. That is actually releasing more carbon dioxide and more methane into the atmosphere because that's locked up in the permafrost. And so that is, again, adding to the problem. Likewise with the Amazon rainforest, actually, if a sufficient amount of the Amazon rainforest is cut down or dies, the entire thing may turn into a grassland. And that critical amount is like, I think 25% or so, but we don't really know. That's because it generates its own weather patterns. And if you cut down enough of it, then it's no longer able to sustain its own weather, and it will dry out, essentially. Lots of really optimistic things to think about. So what do we need? We need net zero greenhouse gas emissions by 2050. That is the UN's Intergovernmental Panel on Climate Change. But every year, the greenhouse gas emissions are increasing. With the exception of this past year where there was a blip due to the global pandemic, but that is not hopefully going to continue. Hopefully the pandemic will not be affecting society to this extent for much longer. And that will mean that emissions are projected to go right back to normal, barring significant action. Okay, so why haven't we done anything? We have done a lot of things. We haven't done nearly enough. Climate change is really, really complicated. It is not a simple issue. People often think of a few particular things as leading to climate change, like flying on planes or burning coal in power plants. And those are really, really important, but there are a lot of important things. This is a division of all the different sectors and activities that are contributing to climate change. And you can see that none of them is actually contributing like the majority. It's not mostly any one thing. Here's like air travel, and that's like a subset of rail, air, ship, and pipeline, and that is just 4% altogether. All of those things together is only 4% of greenhouse gas emissions around the world caused by people. Then there's electricity and heat over here, building, so heating, fuel to heat buildings, manufacturing, industrial processes, agriculture contributing to climate change as a result of methane being produced by cows and other livestock, release of carbon from soils in agriculture, cutting down trees leading to release of carbon sequestered in forests, and many, many other things, all contributing little bits to this massive amount of carbon dioxide and methane that society as a whole is producing. There is no one thing that we can stop doing which will fix the problem. There are all of these many things that we need to change. Now that can be seen as a huge problem, but it can also be seen as an opportunity. There are many ways to have an impact, and each of these things represents a lot of carbon dioxide or methane or another greenhouse gas. And even a small percentage difference is a huge amount of effect. So that is some of the context for climate change as a problem. What does it mean to tackle climate change? I'm often asked, is it too late to tackle climate change? And I don't like this question. Firstly, because if it were a yes/no answer, then the answer would certainly be yes, it is too late. People are already dying as a result of climate change, and we are locked into various effects of climate change now, regardless of what we do. Like, to some extent, bad things are guaranteed to happen, but it's not an on-off switch. Bad things are guaranteed to happen, but really bad things don't have to happen. We get to pick exactly how bad it is, exactly how many people die, and exactly how much of society and global ecosystems are disrupted or destroyed. So there are two kinds of things that we need to do in order to make this less of a terrible situation. First is reducing greenhouse gas emissions. That's called mitigation. The second is resilience to the consequences of climate change, because certain consequences are already happening or are unavoidable at this point, or to some extent are unavoidable. Again, it's all a question of degree. That is called adaptation. So mitigation, reducing the greenhouse gas emissions; adaptation, responding to the effects of climate change. Now, I'm going to be talking about machine learning and AI, and obviously that's sort of what the subject of all this is about. But first of all, let's just think about the role of tech as a whole in climate action. So obviously there are a lot of things being done about climate change and a lot of things that people are trying to do. And we already have technology that could enable our society to have zero greenhouse gas emissions. Why is tech important here at all? First of all, tech is not as important as many other things, like policy. I would not recommend that people go in, work on tech as the best thing to do for climate change, but for the people here, probably, many of us are coming from more of a tech or maybe specifically an AI, machine learning, computer science background. And there are many things that we personally can use our skills for as part of this global picture, recognizing that there are a lot of other things which arguably are more important that are being done in parallel. So why is tech useful as one of the tools to tackle climate change? Tech can make the transition somewhat easier and more palatable for society. So just because we theoretically have tech that could give us zero greenhouse gas emissions, that's not really helpful, because if people aren't going to use that for various good reasons, it requires sacrifices. Even in the best scenarios, attacking climate change requires sacrifices. So there are reasons why people have not changed our entire society. Making that transition easier is really important. It makes it more likely that things will happen. Also providing tools for policy and other needed kinds of climate action. So we will see some particular applications of machine learning AI that help serve other kinds of climate action. And really, that's sort of the broad theme. It's not like tech is going to magically come in and save us. It's more going to help along in little ways things that people have already been working on, but there may be bottlenecks involved. Okay. So the talk that, the things I'm going to be discussing here are from this mammoth paper. It's over 100 pages, called Tackling Climate Change with Machine Learning, that a bunch of us put together to really provide a compendium of recommendations for what are the opportunities for machine learning in tackling climate change and how to think about them. I'm not going to be covering, needless to say, all of this really long paper. I will be discussing some overarching themes, but I encourage people to look at this online if you are interested, and I'll get into some additional resources at the end for those who want to explore more in this space. So the first overarching theme that you can think about for how machine learning and AI can dial into climate change action is distilling observed data. Often there is a large amount of sort of unstructured data out there that can be distilled into usable information. Often this is usable in the sense of providing information to, for example, policymakers, governments, in order to make decisions. So this is not machine learning making a decision. This is machine learning giving people information to make a better decision. Now, where does this massive unstructured data come from? Often that's satellite imagery, remote sensing data, satellite or aerial imagery, or large bodies of text. And sometimes you can take machine learning, you can process this data in a very fast and automatic way, in a way that's much more scalable than it would be if a person were trying to automate all of that, trying to annotate all of that. So some examples here, tracking greenhouse gas emissions. We need to know where greenhouse gas emissions are coming from, how much they are for accountability of different actors and national commitments for international agreements and so on. Satellites can be used to track greenhouse gas emissions with hyperspectral imagery. So if you have a camera that's not looking at visible wavelengths, it's looking at hyperspectral wavelengths, it can track greenhouse gas emissions, things like methane. Methane particularly good because if it's concentrated. So that's something that can be done automatically using machine learning. People are working on. Also pinpointing leaks in things like natural gas pipelines that lead to methane emissions. Gathering infrastructure data. In many parts of the world, we do not know where things like buildings, the electrical grid, solar panels are. And policymakers need that information in order to make better decisions. So gathering infrastructure data on where the buildings are, what are their heights, what are there rough types, energy flow, estimating energy flow within the building to help better understand the space of buildings, because that really affects the energy consumption of different places. That can be done in many cases automatically using remote sensing data. Likewise, pinpointing deforestation in real time as it happens, saying, this forest is being cut down because we have a satellite that's pointed there, or that has taken an image there with relatively high frequency. Evaluating coastal flood risk. There was a recent study that showed that hundreds of millions of more people were at risk from coastal flooding than was previously estimated as a result of very good estimates of the heights of different parts of these coastal areas using machine learning with remote sensing data. And then for natural language processing, parsing large bodies of text, parsing company reports for relevant information can be useful in some cases. In all of these cases, again, taking a large amount of very unstructured data and boiling that down into something that is usable for people on the ground making decisions. Second overarching theme for how machine learning can plug into overarching climate strategies, improving efficiency. So taking a very big and complicated system and optimizing or controlling it in such a way that it becomes more efficient. Now, there are a lot of complicated systems. Some examples of this that are relevant to climate change are controlling heating and cooling systems more efficiently. So that can be within a building, it can be within a residential building, your personal house, like a smart thermostat. But the bigger the building, the more complicated it can be. Google has recently started using machine learning systems to optimize the heating and cooling of data centers. Data centers need a lot of cooling in particular to keep the temperature fairly constant. And that can be done more efficiently using less energy by machine learning. Relatively large amount of energy savings. That is obviously a cost savings in this particular case, but it's also a savings of greenhouse gas emissions if the energy is coming from a source that includes some carbon emissions. Optimizing supply chains is another situation in which there's this complicated system with lots of knobs that you can turn, where machine learning can control the system more efficiently to decrease the distance traveled, to help different kinds of transportation interface with each other. It's like trains are much more efficient than trucks, but if you want to use trucks, you need to make sure the trains and the trucks interface very well, because the trucks are sort of your last mile transportation. The train takes it most of the way, the truck takes it a bit of the way. You need to make sure that you know when the train is coming. You can optimize the schedule scheduling between the two, and optimizing, even the physical packing of stuff, and the routing, choosing which suppliers to use so that you have to transport goods a lower distance. Reducing food waste, similarly, food waste is a massive contributor to climate change. A lot of that food is lost in transportation and storage, but also in just ordering too much food if you're a supermarket or a restaurant. That can lead to needless greenhouse gas emissions for producing that food or transporting it. Having machine learning systems ordering food efficiently for supermarkets, restaurants, other people consuming food at quantity that can predict the demand for a certain thing, so that you don't have to oversupply and so that you don't have as much waste. Demand response in electrical grids, where you have in the electrical grid, you want supply to match demand. And if you have, sometimes you will have more supply of power. So for example, maybe at night, if you have a lot of wind turbines, that might be producing a lot of power. So you might have more power than you need at one time, and that would be a great time to turn on lots of appliances if you could choose when in the day you turn them on. Now, this is the case for a lot of things, for example, charging electric vehicles, but also for a lot of industrial applications. Demand response means moving around the demand in the electrical grid so that it fits the supply and so that it fits the times when the carbon intensity of power is lower. So when there are fewer fossil fuels being consumed to make that power. So demand response is something, this sort of grid scale optimization problem, one of many that can involve machine learning to make it more efficient. Okay, this is the second theme. Let's go to the third theme, forecasting. So planning things, scheduling things, taking time series data and making a prediction of what's going to happen. A bunch of situations where this is useful. One of them is, again, going back to the electrical grid, nowcasting. So we want supply and demand to match each other. But things like solar and wind power depend on whether the sun is shining or the wind is blowing. We need to know how much sun and how much wind they're going to be at a particular point in time. Very high resolution. Very high temporal and spatial resolution predictions that will help us be able to match the supply on the grid to the demand. If we don't know how much supply, then the electrical grid operators have to say, okay, we're going to make a backup and we're going to turn on some fossil fuel generators. This happens. People are running fossil fuel generators on standby just in case the sun goes behind a cloud or the wind stops blowing. That kind of spinning reserve should be reduced. Spinning reserve is the technical term. That should be reduced. And one way to do that is having a really good idea of how much power is going to be produced using very good forecasting, which can involve machine learning. Forecasting agricultural yield to predict famines and food insecurity, predicting prices in carbon markets, which are ways to incentivize people to be emitting less carbon taxes and cap and trade systems. Okay, so that's another theme, forecasting, accelerating simulations. So a lot of AI and machine learning people think that what we need is a better model of the climate. We have a really good model of the climate. We know what's going to happen very well. However, there are ways that machine learning can be useful in helping us model different things, including the climate. It's not by replacing climate models. Machine learning isn't nearly good enough. It's not as good as physics at modeling the climate. We can't just throw a big LSTM at the climate and solve everything. But it can approximate certain parts of those models. There are particular parts of time-intensive physical simulations that are will be very useful to have fast approximations to. So in the case of climate models, there are particular portions of those models, like a radiative transfer, which are really time-consuming. And if you have a fast approximation to that, you can plug that into your bigger physics model and have it run much faster, which can be useful because you can downscale your model. You can make more predictions on very fine resolution. You can say this particular city is going to have this effect for a climate model or a weather model. Weather is just like, day to day, climate is year to year, essentially. Downscaling those models, making much better predictions that can be of use for particular localities, for example. There are lots of other situations where we have a complicated physics model and it's very good, it's completely accurate, but it is very slow. And so we can approximate portions of it using machine learning. For example, in fluid dynamics for modeling the aerodynamics of vehicles, designing more efficient vehicles, and in speeding up electricity scheduling on the electrical grid. So where we have a physics, we have a model of how electricity flows on the grid and how to do that, but having a faster simulation, approximate simulation for it can be really good. Final theme that I want to touch on is accelerated experimentation. Edison supposedly tried thousands of different materials before deciding that carbon was a good material for the filament of a light bulb. We don't have to experiment quite as much if we use machine learning to make predictions as to what experiments are going to go well. This is not a replacement for scientific experimentation. This is a way to suggest experiments to try. So some examples of situations where this can show up are in designing better materials for batteries, which are really fundamentally important if we're going to have more renewable energy. Storing energy when the sun is not shining or when the wind is not blowing, really important to have good battery technology. Suggesting materials that might work for batteries so we can test those out and see if they do work. The paradigm being run some experiments, see the results of those experiments, feed them into a machine learning model. The machine learning model suggests some new experiments for you to try. That can speed up the process a lot. Likewise for designing more materials for solar panels, synthesis methods for very energy intensive processes like making industrial scale fertilizer and other things. Okay, so those are some themes for how machine learning can dial into climate change relevant strategies. And I'm sorry?
Hi, David.
Hi.
Sorry to cut you off. We are reaching towards the end of your segment here, so if maybe you just wanted to wrap this section up, we have a couple questions.
I was told I had 5 more minutes, so I should, and that there would be a Q&A at that point. So I will finish in the next 5 minutes, and then will be Q&A. Absolutely.
Perfect. Thank you.
Yeah. So I want to now touch on how to think about machine learning and climate action. So in each of these cases, machine learning is only one part of the strategy. It is not the entire thing. And it is really, really important to remember that many tools and skills are necessary to fight climate change. Machine learning is only one of those. Many areas do not need machine learning at all. In all of the things we saw before, machine learning is only one part of the puzzle, but in some cases it's not a part of the puzzle at all. There are many examples, like hydrofluorocarbons, where there isn't really an application of machine learning, even though it's a really important thing that people need to be working on to tackle climate change. In some cases, there are very low-tech solutions that one needs to work on first. Like, for example, in buildings, if you are designing, if you're trying to make a building more climate conscious, you want to insulate it. That is the more urgent thing than giving it all kinds of smart sensors and having it be machine learning enabled. Make a smart building, that is great, but the low-tech solution is much more urgent and much bigger impact. Even when you are working with data, sometimes simple methods will work. Don't reach for a fancy, complicated model first. Reach for the simplest possible algorithm, then make it more complicated if you need it. This is really, really important. Don't jump for fancy tools. The impactful applications are often the least sexy ones. The things that people don't necessarily talk about are often most impactful. Things like freight routing are not necessarily going to be buzzwords, but they're much more impactful than something like self-driving cars from a climate perspective. Self-driving cars are actually probably going to make the climate worse because they'll probably lead to more driving, which gets at another thing. Jevons paradox. So the Jevons paradox says that if you make something more efficient, you don't necessarily make a better, in this case, climate impact, because you can cause people to use it more. Self-driving cars are probably going to lead people to drive more and lead to a greater climate impact. Incentive alignment, profit is also not the same as climate impact. Just by having a roughly green sounding business that's making money, that does not necessarily mean you are having an impact on the climate. And it's also important to remember that machine learning is not intrinsically either good or bad. There are negative applications too. People are using machine learning to accelerate oil and gas exploration and extraction, and that is assuredly making climate change very much worse. Machine learning is a tool, it matters how we use it. Now, how should you think about machine learning and climate change projects? First, you should think about the context within broader climate change strategies. It's important to understand where this lives within climate action. Next, you need to think about the specific bottleneck, the specific problem, why ML is needed, and then work on matching the techniques to the problem that needs to be solved. Start with the problem. Don't start with a fancy technique. Then you can think about the ML methodology, but also think about the pathways to deployment and impact. Make sure that you're not thinking about just coming up with a nice algorithm. From the start, you need to be thinking about how it's going to actually be used, working with the right partners, scoping with those partners to make sure that it has a pipeline for impact. And then think about general considerations. There may be side effects, there may be ethical or social considerations. The overall way in which you can have all of these 5 points is to work with partners, work with and talk with a lot of people who are in the relevant domain. There are lots of different people you should be talking with. You should be talking with researchers in the relevant domain. So if you're working on an energy project, talk with energy researchers. If you are working in really any of these contexts, you should be talking to the companies who are going to deploy the technology, or the other entities, if it's governments. Talk to the people who will use this. Make sure you understand what they need, because if you don't from the start, then you may be building the wrong thing. The companies, the people who deploy it, are generally different from the researchers. Also think about the communities or the end users for whom it is deployed. Those are different interests than the companies who are deploying it often. Think about also the policymakers who regulate the technology. And sometimes there are different interactions with policymakers. Be aware of what they need as well. I realize this is a lot of different pieces to consider. Working with collaborators who are in the relevant domain, they will understand more of these pieces because they do it every day. Don't make a project which is just machine learning people talking to themselves. That is a great way to have no impact at all or be counterproductive. Work with domain experts from the start. Don't just bring them in after you've created something. Work with them in the initial scoping and the development, not just the deployment. If you're working with them from the start, you can make sure you're designing the right thing. If you build something and then look around for a place to apply it, that's the wrong order. You need to work on what you are building before you build it. I know that Dr. Sasha Lucioni, who's talking next, is going to talk about this more. And finally, I want to touch on more resources, just to conclude. So I am one of the founders and chairs of Climate Change AI, which is a volunteer initiative from people around the world working to catalyze work at the intersection of climate change and machine learning. So we have global network, thousands of experts in all the different pieces of this, so research, industry, and policy. We have a lot of resources for working in this space. So in addition to the paper, which I mentioned before, which was written by Climate Change AI, we have a lot of other resources. We have interactive summaries of the paper, so you can find particular areas to work in that match your techniques of expertise. We have a newsletter you can sign up for with jobs and funding opportunities, papers, and data sets coming out on a regular interval. We have a discussion forum where you can talk with other people, ask questions online. We also have physical events for knowledge sharing. They are digital now because of COVID, but we have a regular series of events like workshops at NeurIPS, ICML, and iClear, so big machine learning conferences, also at other places like the UN Climate Change Conference. And recordings of past events are in general available online. We also give advice to relevant stakeholders like governments and companies. I am happy to take your questions. Thank you so much for listening.
Awesome. Thank you so much, David.
There's a question about comparing AI with statistical analysis. I mean, some of this is mincing words. Like AI, a lot of people, when they say AI now, mean things like deep learning, but AI also includes arguably things that are also sort of statistical analysis. There are a lot of Bayesian methods in AI, a lot of things like random forest. Statistical analysis is often good because it's interpretable. So there are various reasons why, various things that you often want in an application, in certain kinds of applications, to have greater adoption. So one of those is interpretability, understanding why your algorithm is making a certain decision. That can be an advantage of a method a Bayesian method. You can understand a bit more why it's making the decision. You can also have a better quantification of uncertainty. It's really good to know not just what the prediction is, but how confident you are in that prediction. So those can be really important. As an example, I was talking with somebody who developed a really great reinforcement learning algorithm for controlling the temperature of a skyscraper in Manhattan. And it was a really good algorithm, but the building operators were not using it. And the reason was because they didn't trust it. And what happens in such a situation is, you have this algorithm and you try to deploy it. And the people are like, I don't know why it's making this decision. At least if you have a big, black box reinforcement learning algorithm, which is what I assume this was. No reason to know why it's making this decision. So the human operator is like, what if I do this? I don't really trust this AI thing. And so then, they tweak a little thing and the AI tries to compensate for that. And the humans are like fiddling with more knobs and the AI freaks out and it goes into it hasn't seen, it doesn't know how to interact with humans. So, it's not interpretable and it doesn't have good human interaction skills, as it were, can't deal with out of distribution data. And so the algorithm stops working and the humans stop trusting it and you've done nothing. So greater interpretability and realizing how something is going to be used in practice is really, really important. Sometimes greater interpretability can go along with more statistical approaches. Sometimes that's not relevant. There are a lot of good approaches for interpretable AI that don't require that now. But yeah, something you bear in mind. More questions?
I believe that's all the questions we have at the moment, but if any of our attendees would like to post any questions later on, we will be sure to post them in our Slack channel and pass them along. So
fantastic.
Thank you very much, David. That was a great presentation and we really enjoyed hearing from you. We have a few minutes now. We're going to take our break before we come back at 6:40 for our next speaker. So if everyone would love to take just a few minutes to grab some water, take a breather, we'll be back at 6:40. Thank you.
All right, so we're back. I hope everyone had just enough time to take a short break. We're trying to manage to stay on time as much as possible, given that it's a very packed schedule and all kinds of people from different time zones means it's getting very late for Europe and of course Asia as well. So thank you again to Dr. David Rolnick. Really appreciated that presentation. Glad that you were able to finish that. But yeah, we were just kind of thinking that we would try to have to be firm on time so that we don't make the other presenters late. So let's go to our next presenter, keynote presenter, which is Priya Danti. And she's a PhD student in computer science and public policy at Carnegie Mellon University and US Department of Energy Computational Science graduate. She is a co-founder and chair of Climate Change AI, and her research explores ways to incorporate domain knowledge into machine learning models. Thank you so much for being here, Priya.
Oh, can you hear me?
Yes, now we can.
Oh, awesome. All right. Sorry for being muted. Hey, everyone. Thanks so much for having me. As to be mentioned, my name is Priya Danti, and today I'll be talking a little bit about some of my PhD work, which deals with incorporating physics and domain knowledge into deep learning, specifically for climate change related applications. So as David gave a great overview of in the previous talk, there are many, many different ways in which machine learning can be used impactfully to tackle climate change. And I'll argue that there's even though there's a really diversity of problems that machine learning can be used for and a real diversity of ways in which these need to be tackled, there's one thing that is in common between all of these different applications. And it's that they interact with the domain in which they're implemented. So if you're implementing something in electricity systems, you're going to be interacting with stakeholders in electricity systems who have built up a lot of knowledge about how electricity systems work over the years. Same thing with buildings, transportation, climate modeling, societal adaptation, anything. Your machine learning method will be kind of integrated into some existing domain. And so that sort of leads to the question of, if we're using machine learning in a particular domain, shouldn't we actually incorporate knowledge from that particular domain? So what I mean by that is machine learning to date has actually experienced a lot of low-hanging fruit successes. So in tasks like image recognition, labeling various images, sort of just feeding images into machine learning models, seeing what those machine learning models learned, and then coming up with some kind of machine learning algorithm based on that just worked. These pure data-driven methods sufficed, and we were able to actually kind of throw out a lot of existing knowledge about, for example, images or even language. We have a lot of kind of deep learning models that are being used for language modeling at the moment that are not necessarily using traditional linguistic reasoning kinds of things. But I'd argue that we've actually kind of, exhausted some of those low-hanging fruit successes. And a lot of the remaining challenges that we'll have to face, including many in climate change, are much harder than that. In particular, there are a lot of domains where there's a smaller amount of data, or where you have to satisfy the physics or hard constraints of that system. For instance, if you don't satisfy the physics of a power grid, you're going to get a blackout. Or where your methods have to be interpretable. Maybe they're interfacing with human operators or human decision makers who have to be able to trust and understand what your method is doing. And so in all of these cases, one way to kind of move forward on addressing these challenges is to combine machine learning methods with other knowledge and other methods, rather than just going for, in some sense, pure machine learning based methods. And there are a lot of different ways to do this. Today, I'm going to just cover kind of one way to do this, which is kind of through a method called incorporating implicit layers into neural networks. But at the end of this talk, I'll sort of zoom back out and talk about some other ways in which one can do this, kind of incorporate domain knowledge into the way that we do machine learning itself. So since the specific kind of way to do this I'm going to talk about involves neural networks and deep learning, I'm going to just give a 2-slide overview of what deep learning is before going into some more details about my work. So many of you have probably seen a picture like this at some point, which is meant to represent a neural network. So you have some input X, you have some kind of fancy little functions that X goes through, some string of functions, and then you have some output Y. And what's really going on here in this kind of abstract picture is that what a neural network actually is a bunch of functions strung together, a bunch of functions composed together. So each of these little traffic light looking things is actually a function, and you can sort of think about you have an input to your neural network. You have an input to this first function here. It spits out some output. That output goes into some next function, which spits out some output, and so on until you get your final output here. And importantly, these functions tend to be non-linear. They tend to be a little bit complicated. That's what makes neural networks overall be able to kind of capture complex functions. And importantly, each of these functions is differentiable. You're able to take derivatives through it. And that's sort of the kind of crux of what a neural network looks like. You have a bunch of functions strung together. These functions are kind of non-linear, a little bit complex, and you can take derivatives through them. And the reason especially this last part about taking derivatives through them is so important is because of the way in which we update neural networks. So in particular, you usually look at the output of your neural network. You see how good that output is, some notion of error or cost. And then you use information about the derivatives of that error to kind of update all of the parameters of your neural network, basically to update the kinds of functions that your neural network is representing. So for those who know about deep learning, that is obviously a very basic and high level thing, but I just wanted to give this overview to basically say that if you want to use a neural network, every single thing in your neural network has to be differentiable. And in a moment, it'll hopefully become clear why I'm emphasizing that point so much. So just to give an example that I'm going to actually bring back later on in the presentation, imagine that you were trying to forecast electricity demand on a power system. So you might use some information like past demand or weather or time. These are the features of your model. You might be trying to predict future demand, maybe with some error bars. And you might use a neural network to try to figure out the relationship between these inputs and your demand forecast. And you may be trying to optimize some objective, for example, to minimize the error of your demand prediction. And that optimization problem might look something like this. You're trying to pick some parameters for your neural network so that when you put inputs into that neural network, the estimated demand it spits out is close to the true demand. And you would kind of iteratively update you'd start with some initial guess for your parameters, and you'd iteratively update your parameters based on some derivative information. Okay, so that's kind of the 2-slide high-level overview of deep learning, basically lots of differentiable functions, and one way you might use it, for example, is to create predictive models in this particular way to minimize the error of the output of the model. Okay, so I'm going to switch gears a little bit and now talk about power systems. So electric power systems are kind of the backbone of a lot of what we do. The lights that you're viewing me with right now are powered by electricity. And one kind of challenge that we're seeing in electric power systems is that really they're a really delicate balancing game. So the amount of electricity that is produced on the power grid has to exactly equal the amount of electricity that is consumed on the power grid at every single moment. And this is really tricky, actually. In particular, if I'm consuming electricity, I can decide to turn my lights on or off at any moment. So it's kind of impossible for an electricity system operator to exactly know how much electricity that I or others will be using at any given time. Similarly, electricity production is not fully controllable either, especially as we have more solar power, wind power, other renewables that are coming onto the electricity grid. These things depend on weather. The amount of solar power you get from a solar panel depends on, for example, how strongly the sun is shining. And so you can't entirely control electricity production anymore either. And so figuring out how to create a balance between electricity supply and demand is actually a really challenging problem, and one that is really critical to integrating renewables at a large scale into the power grid. So the kind of way in which electricity system operators actually schedule electricity on a power grid, the way they actually kind of figure out how much power certain power generators should produce based on the amount of renewable energy that's available and the amount of demand for power that there is. There is an optimization problem called AC optimal power flow that these power system operators tend to solve. So this is the form of that optimization problem. Grasping the details of it aren't necessarily important, but the goal is basically to figure out how much power each power generator should produce in order to minimize the costs of power production, but still respect the constraints and the physics of the power grid. So this is the optimization problem that's used there. And so I motivated this talk by saying that it's really important when we're kind of doing machine learning methods and deep learning methods to incorporate knowledge about the area in which we're working into these methods themselves. And so the reason I showed AC optimal power flow, this power system optimization model on the previous slide, is because I'm going to argue that there is a way in which we can integrate it into neural networks, and this can actually unlock a lot of different applications in the power sector that we couldn't necessarily do before. And so the way this works is, again, we have this neural network, which is a bunch of functions strung together, and we just replace one of those functions with our power system optimization problem. And that's it. And of course, there's some challenges in doing that and some kind of math you have to do to actually make that work. In particular, earlier on, I was kind of emphasizing that every single function that is in a neural network has to be differentiable, and sticking something like AC optimal power flow, sticking some optimization problem into a neural network isn't as exempt. We have to figure out how to take derivatives through this optimization problem. At a high level, what we do is we write down what are called the KKT conditions of that optimization problem, which basically characterize its optimal solutions, and use something called the implicit function theorem to take derivatives through those. If you didn't follow that, if you're not familiar with optimization theory, do not worry about it at all. But the basic idea is that the reason we're able to stick this power system optimization model into a neural network is because we are able to figure out how to take derivatives through it, and we do that using various concepts from optimization theory. So this kind of approach of honestly just sticking power system optimization models into neural networks can unlock a couple of different applications. So one of them is an application I'm going to call decision-driven forecasting. And this is the idea that to come back to this example I talked about earlier of forecasting electricity demand with neural networks, often what we do when we create these kinds of predictive models is we sort of try to make these models as accurate as possible. We just say, if we can forecast demand and our demand forecasts are close to the actual demand, then we're done. And we can sort of create that model, package it up, give it to electricity system operators, and they can use it. But this is actually, in some sense, a little bit removed from what electricity system operators actually care about. They don't care about how accurate the demand forecast is, ultimately. What they care about is, when I create a demand forecast and then use that to optimize the power system, is the way in which I optimize the power system, is the decision that I actually made based on that forecast any good? And so one kind of application that you can actually unlock by incorporating power system optimization models into neural networks is actually allowing your electricity demand forecasting model to actually optimize for this, to optimize for the quality of the decision that's made on its behalf. So to kind of put that in math, basically, before I sort of talked about this example objective that your neural network might be optimizing. So you might be optimizing for some loss or error between your estimate from your neural network and the true electricity demand quantity you were trying to forecast. But now instead, what we're doing is we're asking, when I make a prediction of electricity demand, how am I going to schedule electricity generation based on that? And now, instead of optimizing for accuracy, I'm going to optimize for the quality of the electricity generation schedule that was created based on my forecast. So this in math is what this is showing here. Basically, if we had some inputs to our neural network model and some parameters for a neural network model, we would create some demand forecast, and the electricity system operator would make a decision, Z, based on that. And what we ultimately care about is how much that decision costs when applied against the actual electricity demand. And sort of how this looks in now kind of the neural network model is that we had this neural network before. You can think of the inputs as being sort of, again, past weather, all of the features that you're using to make your forecast. This output is the demand forecast. And then you stick that demand forecast into the power system optimization model. You get the decision that the power system operator would take. You calculate the cost of that decision against the actual electricity demand, and then you update your model based on all of this information. And the upshot of doing it this way is that it really does actually help electricity system operators make better decisions. So in particular, what I'm going to throw up on the slide here is on the left, we have our network with the solid green line, and a kind of accuracy optimizing neural network in the dashed red line, where the x-axis is the hour of the day for which we're making a forecast, and the y-axis is the error of that forecast. And in this graph, what we basically see is that the neural network that is optimizing for accuracy does better when it comes to accuracy. Lower values here are better. And our network is actually a little less accurate than the other network. But when you actually compare these two networks on the basis of cost, so on the right graph here, the y-axis is now the cost of scheduling power, you see that our network actually incurs far lower costs than the accuracy optimizing network, actually by about 40%. So by sacrificing accuracy, we're actually allowing our network to, it's making mistakes where those mistakes are not super costly for a power system operator, and it's not making mistakes in cases where it's really critical that those forecasts be accurate. And this is sort of enabled by kind of incorporating power system optimization and knowledge about the way in which power system operators make decisions into the neural network. So I know I'm sort of starting to get close to the end of my time, so I'm going to breeze through the second application here, which is understanding the parameters of the power grid. So at a high level, there are a lot of cases where the parameters of the power grid are either unknown or not disclosed. So this happens on the part of the power grid that's near homes and businesses called the distribution grid, where historically we haven't had a lot of sensors. But now, because we're starting to install things like rooftop solar, we need to understand what's going on. So there's a whole area of study called state estimation and topology estimation that tries to sort of derive information about the electricity distribution grid based on the few sensors that we have in order to help us optimize that system. There are also a lot of cases in which power grid data is kept private for cybersecurity reasons. For instance, if certain parameters of the power grid are made public, that might allow an adversarial actor to come in and cause a blackout on purpose. So for both of these reasons, there's actually a lot of work in trying to estimate the parameters of the power grid. In the first case, to basically allow us to optimize power grids better. And in the second case, to basically do vulnerability assessment, to understand what information might actually be public that we didn't think was public, and allow us to then design kind of more robust power system optimization algorithms. And So basically what we can observe is that in general, at least on the US power grid, there's some information, specifically power generation and power prices, that tend to be known. And there tends to be other information, things like maybe the structure of the grid or the actual amount of money it costs each power generator to produce power. These things tend to be unknown. And yet we actually do know the relationship between these two things. We know that they're related via AC optimal power flow, or they're related via the physics of the power grid in some way. And so what we can do is actually write down an optimization problem called inverse optimal power flow, which is basically saying, if I can figure out what inputs to AC optimal power flow actually would imply the outputs that I actually see on the power grid. So if I put some guesses of inputs into this power system optimization model and I get some guesses of outputs, if those guesses for outputs are close to the actual quantities I observe on the power grid, then maybe my inputs to AC optimal power flow, maybe my guesses to the inputs of AC optimal power flow were actually correct. And so the way we do this in a neural network setting is we basically say, we again kind of replace a function in our neural network with AC optimal power flow. We let the input to our neural network be the power demand. The parameters of our neural network are actually going to be the quantities that we don't know. So in this case, power costs and the grid structure. And the output of our neural network is going to be the stuff that we estimates for the stuff that we actually can observe on the power grid. So this is power generation and power prices. We then, given a current guess for the unknown quantities, we then compute the cost. We compute, sorry, the error between the output of our neural network, sort of the estimated output of our neural network, and the actual quantities we see on the grid. And we iteratively update these guesses using derivative information until we're done. And the kind of upshot of this is basically that we are actually able to recover information about the costs of power generation here with very little data. But we're actually not necessarily able to recover information about grid structure. I know I'm not necessarily explaining these graphs, just I want to make sure to leave some time for questions, but I am happy to share the slides with anybody afterwards who wants to take a closer look at these graphs. But basically some information is recoverable, but other information might be harder to recover. So kind of stepping back for a second, I again motivated this talk by saying that it's really important to incorporate domain knowledge into machine learning methods. And this is one example of how you would do that, by kind of sticking power system optimization problems or other kinds of optimization problems into neural networks. But I do want to emphasize that it really is only one way to think about this issue. So for instance, I talked about power systems, but there are other physical domains like climate science, where it makes sense to incorporate information about climate science into neural network models. And there are actually kind of various mechanisms, something called, for example, neural ODEs, which could be a good direction for doing this. And then there are cases in which other methods entirely are appropriate. For instance, incorporating indigenous knowledge into machine learning to do things like create sustainable land use strategies. This isn't necessarily about sticking a scientific, sticking a physical equations or an optimization problem into a neural network, but it can be about a lot of other things, like what kinds of questions are you actually asking with your machine learning model? What kinds of data should be used? Information about the structure of the neural network model or machine learning model, and so forth. There are a lot of things about a machine learning model that should be shaped in these cases by, for example, indigenous knowledge. And in general, this kind of whole thing of incorporating domain knowledge into machine learning is only, of course, a small part of the full pathway to impact. So David talked about this before, and I believe Sasha is going to go into it in more detail after this. But of course, you want to be working with stakeholders to make sure you're scoping your problem correctly, that you're analyzing its impact properly, that you're really thinking about the downstream consequences. But in general, I think that integrating domain knowledge into machine learning methods is sort of one small stepping stone to better integrating machine learning and various climate domains. So if you were interested in some of the aspects of this talk and want to learn more, so the 2 papers that this talk was based on, the titles are listed on the slide and they can be found on my website. If you're interested in this general concept of sticking optimization problems or dynamics equations or other kind of more complicated things into neural networks, I'd encourage you to check out this implicit layers tutorial that was given at the NeurIPS Machine Learning Conference last month. And if you're generally interested in just the various ways in which machine learning and climate change intersect, I know David already gave a pitch for this, but I really would encourage you to check out Climate Change AI. Come to our happy hours to meet collaborators, come to our workshops to learn more about some of the cutting edge work in this domain, check out our tutorials online and so forth. And with that, I'd like to thank you so much for listening. I am happy to take any questions, and also please feel free to reach out to me after this talk if you have any additional questions too.
Awesome. Thank you so much, Priya. That was really inspiring and great to see where AI can really make a difference in terms of lowering the CO2 emissions. I'm going to ask Shida, are there any questions from the viewers or participants?
Yes, thank you, Priya. That was a wonderful presentation. We have 2 questions here, so I'll start with the first one. It's how does this methodology compare against stochastic optimization approaches? What would be the advantage of using this method instead of a demand forecasting approach embedded in a stochastic modeling or programming model?
Yeah, so that's a wonderful question. And I'm assuming this is kind of relating back to the task-based forecasting method that I was talking about earlier. So as you'll actually see from the title of the paper on the slide, we actually do employ this framework within a stochastic optimization model. So we actually predict a kind of probabilistic demand forecast where you predict actually the demand and then the uncertainty bars on it. And then you can stick that into a kind of probabilistic programming optimization method. So I wouldn't say these viewpoints are mutually exclusive. I think having uncertainty aware forecast is really useful. But I also think that even if you have an uncertainty aware forecast, sort of the assumptions you make there, for instance, you might assume in your uncertainty aware forecast that you're dealing with a Gaussian distribution and the distribution may slightly be different in a way that affects the optimization outcomes. It's hard to account for all of these things ahead of time. And so if you have knowledge about how that even stochastic forecast is going to be used in the context of a stochastic optimization model, you can still kind of play the same kind of game of understanding how good the output of that stochastic optimization model is in order to then inform the way you make your forecast in the first place. So yeah, stochastic optimization is awesome and I think can be combined really well with this kind of framework.
Wonderful, thank you so much. And the next question was, if you use a supervised learning, the difference between your estimation results and real data would be very small. Did you apply the model into a new data set?
Yeah, it's a great question. So we actually, we do like split between training and testing data as one often would. But I guess one thing I'll emphasize is going back to the relevant slide is that even for a model that is relatively good, you'll actually see these root mean squared error numbers are actually really low. Even for a model that's relatively good, it can still make critical mistakes that can really affect the optimization outcome. So for a power system optimization, this is something like if you predict that your demand is, if you under predict demand, your kind of demand prediction is too small, an electricity system operator might under procure supply, they might purchase too little power, and then not be able to compensate for that because there are some physical constraints on how much your power generators can change from time to time. They may not be able to compensate for that in the next time step. And that has potentially worse consequences than over predicting and wasting power. But the idea is that even if your prediction is good, if it's maybe even slightly off, but in the wrong direction, that can actually have quite cascading effects on the power system optimization. And so that's why it makes a lot of sense to, again, sort of take that optimization model into account.
Fascinating. Thank you so much. If there's time, there is one last question from our YouTube live stream. The question is, have you ever included functions into the middle of the network rather than into the cost function?
Yeah, it's a great question. So in both cases that I showed, the places I embedded the optimization model are places where I kind of knew either what the input, I knew what the input to that model represented. And in this case, that was kind of important because you, if you're, for example, sticking parameters into your optimization model or inputs into your optimization model, you kind of want to make sure that they actually represent the quantities that you think they represent. That said, there is actually quite a lot of work that hasn't used this particular optimization model, but other optimization models that have just stuck random optimization models as layers into neural networks instead of other functions. And they have found some success in various domains. I think you do potentially lose, if you don't have a principled understanding of what is coming into the optimization and what is coming out, then you do lose some of the physical interpretability. You might just get a more powerful neural network layer, but it may not be as domain integrated. So, but yeah, if folks are interested in trying that out, a lot of my code for these things is online and I'm happy to share it. So I would definitely be curious to see if folks were sticking this into neural networks in other places, what would happen.
Amazing. Thank you so much. That was very enlightening, and I'm sure people will be sure to find you online and hopefully reach out if they are wanting to find out more about this. I'll pass it back to Tim to introduce our next speaker. Thank you.
Yeah, thank you so much, Priya. Again, really lucky to have you. And next, we're also very lucky to have Dr. Sasha Lucioni. Sasha is a PhD in cognitive computing in 2018 and a researcher working on artificial intelligence for humanity initiatives at Mila Institute. She leads projects at the nexus of AI and social issues such as climate change, and she has organized many AI for social good initiatives, conferences, and workshops. Thank you so much, Sasha, for being with us.
Thank you. Let me share my screen. Can you see my presentation?
Yes, we do.
Good. So thank you for having me. I know it's been a long day for you and you have a big weekend up ahead. So my goal today is to inspire you a little bit in your projects, to give you an idea of essentially how to take ideas and bring them to impact in terms of AI and climate change. Now, David and Priya have already given us amazing ideas and guidelines to follow and kind of best practices to respect. But I thought that it might help you to kind of tell you my story in terms of getting involved in AI and climate change and essentially how that all happened, and hopefully you'll get some information for your own ideas and projects. So a question that is often asked to a lot of us is, I want to use ML, AI to move the needle on climate change, and where do I start? So David gave such a great kind of cornucopia of different things that can be done with machine learning. But more concretely, I wanted to talk about my own project. And so it started with an idea. This is Joshua Bengio, my supervisor. And now 2.5 years ago or so, he had this idea that, this is actually a slide he presented back in 2019, creating a viral app to visualize the future and emotionally anchor essentially climate change. And so the idea at the time was to take climate models and to essentially personalize them in order to create like a user-based visualization. So his idea was, take all these models, take their predictions, travel into the future and see what your house will look like in 2050. And so the idea was to, show houses, show pictures of people, and to kind of have this viral aspect of it. And the idea by Joshua was that that would be pretty straightforward to make, and could have a big impact in terms of, raising awareness of climate change. So that was the idea a few years ago. And the technology that he had in mind. So in order to do this kind of generative approach, right, you're creating new things. And the architecture in machine learning that's best suited for this are generative adversarial networks, or GANs. So just to give you a general idea of how it works. So essentially a GAN is two neural networks playing against each other. So they're essentially competing. So one is trying to fool the other, generating essentially images, and so that's the generator. And the discriminator is saying whether they're real or they're fake. And so at the beginning, essentially the generator starts with random noise. So the discriminator really can say, this is fake, this is fake, this is fake. And then at a certain point, going through the training set, right? These are images of digits, for example. So going through the training set, the generator learns what constitutes a 1 and a 2, because you have the labels for each image. And then eventually it starts producing things that are plausible. And now the discriminator gets fooled. And so this game keeps on going essentially until they reach like a Nash equilibrium, essentially when they're both kind of at their local or global minimum. And so GANs are pretty hard to train, technically very powerful, but often take a lot of training data and quite a lot of time to get the right fit, and lots of losses and lots of kind of more technical aspects of them. But they have achieved results like this. So these are all people generated by GANs, fake people that don't exist. So now you can create really, really high quality images that are kind of really realistic, right? So this is kind of one of the applications of GANs, deepfakes and things like that. But another applications of GANs are conditional transformation. So instead of just randomly sampling through a data distribution, essentially learning what constitutes a human face and randomly generating this human face, you learn what transformation is essentially transform, for example, horses to zebras or vice versa, photos to Monet paintings, summer to winter. So the idea is here that you have two distributions in your GAN training, and essentially you're learning a transformation. You're not learning like a generation from scratch. You're learning really how, given this image, to transform it into this other image from two different distributions. So this is called Cycle GAN. Actually, this came out essentially 3 years ago, and then when Joshua Benji saw this, he had an idea that, well, if you can transform summer to winter, maybe you can transform kind of places that are not affected by climate change to ones that can be. So this was kind of the big idea. And me at the time, I was working in banking. It was a really cool job, but on the other hand, I felt like I wanted to do something about climate change. Kind of like all those people now who ask me, what can I do? How can I get involved? I was kind of like, I don't know what to do. You know, I compost, I don't eat meat, but how can I actually make my work aligned with the things that I care about? And so I decided to take a leap of faith, and I essentially worked evenings and weekends to get a prototype of this idea of Joshua's up and running. And essentially I got some images of some floods. I tried to train a cycle GAN with a very limited amount of data. And I called it Karma GAN, essentially karma out to get us if we don't take necessary action against climate change. And despite the very terrible results, Joshua decided to give me a shot. So I quit my job. I decided to leave Morgan Stanley and go back to academia. And it was obviously a big change. And I know that for some people, it's just not a choice. But what I personally felt is that doing things halfway was not enough for me, that I really wanted to dedicate myself to this kind of 100%. And so February 2019, I decided to start a postdoc at Mila around this project. And of course, I wasn't alone. So this is another part of what David and Priya mentioned. It's very rare that one person is enough, or I would say never enough to actually, build a project from scratch. So we hired behavioral scientists, machine learning experts, climate scientists. We hired this whole team for different aspects of the project. And actually, this has been going for 2 years. So now we have another set of interns and students and et cetera. We're working with a professor at University of Montreal on the psychological aspect of our images. And so just to tell you that, this team at some point was like 15 people, and all from different disciplines, and kind of learning how to work together, learning about each other's science, about each other's domain knowledge. So this was a lot of translation and a lot of kind of understanding of different disciplines. And also something that we realized is that it's really, really hard to take climate events and downscale them to a granular level like we initially had in mind. Essentially, we're not there yet. The science is not there yet. And also there are so many things that can change, right? It's not 100% sure what's going to happen. There can be feedback loops, like David mentioned. So it's really hard to predict the future in 2050 in terms of climate models. So essentially, we published an initial paper of actually using cycle GANs as well, using a little bit more data than I initially had. So that was a first step in terms of machine learning. And then we started iteratively working through our project. So we worked on the climate models for a good year, and then we realized that it just wasn't possible. So we moved on to a different version of our project and learned from that. And I think also kind of made us, it made us more aware of what the science can and can't tell us at this point and where we can go with that, right? So we moved on from CycleGAN to Munit, another architecture. You can Google it. It's a really interesting architecture that disentangled content and style. And so the idea between Munit is, okay, you have two images, and instead of just transferring one to another, like horses to zebras in CycleGAN, you're going to try to disentangle, you're going to try to separate what constitutes the content of the image and what constitutes the style. Like, for example, if you're, transferring Monet's style, that's really the style, but all the objects in the image, that's the content, and you don't want to touch the content, you only want to touch the style. So we did that for a while. It worked fairly well, but we still kind of hit a wall in terms of, the disentangling the actual contents of the image, because we realized that flooding, for example, the first phenomenon that we're working on, actually impacts more than just the ground. It's actually more destructive because like the water can go up. So essentially that at a certain point we hit a wall. So we spent a good 6 months on that. And then we use an architecture called Instagan, which also worked fairly well, but once again, using kind of like like the content of the image and the style of the image, we were able to get some pretty cool looking results. This was like back in I guess summer of 2020. We got these results, but once again, we hit a wall because we couldn't make the whole of the image transform the way we wanted to. So really, it was kind of like a nice little paintbrush painting the ground, but nothing more. And so this is really tough. I think that for a good couple of months, we were kind of in a rut and thinking that we were going to get there, and that our algorithm is not robust enough. That first the climate models weren't possible. Now the machine learning isn't possible. And then essentially, in the fall, we had a new group of students come in, new energy, new ideas. And we decided that, when you hit a wall with one single approach in machine learning, maybe you can split it in two approaches. So sometimes when a single model doesn't solve a problem, a multi-step approach will. And this is a bit of an engineering way of looking at things, right? Because in machine learning, you really like these elegant solutions that are a one solution for the whole pipeline, and that makes sense, that are sophisticated. But what we realize is that because we're making really a tool that has to be deployed, that has to be robust, that has to be really like no matter what image you throw in, it has to work, that maybe a two-step approach will actually work better. And so we divided our problem into two aspects. So essentially now we have two GANs. Two GANs are better than one. We have a masker, which essentially takes an image, and actually what we're doing now is we're taking the segmentation mask. So essentially a segmentation mask, it tells you what kind of objects are in the image. And we also have, so these are essentially pre-trained neural networks that can detect like cars and humans and buildings. So we're using some pre-trained models. We're also using a pre-trained model that will detect depth, because we realize that sometimes images are really facing a building and it's very square and very like you can really see exactly everything, and then sometimes it's a perspective, so you've got like this street going far away from you, and then you need the depth in order to be able to parse that scene, to project in that scene. So essentially now we have we have a segmentation mask, we have a depth mask, we have the image itself, and essentially based on images of flooding, our masker model learned where water should go, right? But it's not painting the texture, it's just painting like what you see here, a gray mask saying this is where water should go in the scene. I looked at the depth, I looked at the objects, this is my decision. And then we have another network that takes that mask and then looks at the rest of the image and says, well, okay, well, this is the mask, and then these are the other objects in the image, and then this is what the water should look like. So now we have a masker and a painter. And actually, impressively enough, we ended up having a much more robust architecture that works a lot better. And also in the recent months, we've added other events. So on top of flooding, now we have smog, which is a very kind of a very prevalent event, and wildfires, because sadly recent events in California, Siberia, etc., gave us a lot of training data of wildfires. And so now we're actually in pretty much the final stretch in terms of results after 2 years. We have some really realistic looking images that are robust. This is actually Montreal. So no matter what the scene, pretty much no matter what the scene we throw at it, the network knows what to do. It even does reflections, it does color, see, so the painter sees the yellow and reflects yellow in the water and the white and the brown, etc. So we've gotten some pretty good flooding going on. Smog is work in progress a little bit. We're trying to figure out the depth issue to have, smog being denser when it's closer to you than far away. But still, it's kind of, we're working on it. As you can see here, like you see some different levels of smog. So that's something we're still working with the colors. Colors are an issue. Wildfires as well, as we've seen from images in California. Often there's like this orange or orange or red kind of this also kind of a smog, but it's more from the sky, right, than from the ground. And so we're also playing around with depth and sky and trying to figure out what the best way of representing that is. So essentially the machine learning part is almost done. And what we're working on now is actually turning out to be almost more complicated than the machine learning. It's creating a website. So now that we have this cool package, as David said, it's not enough to just have the cool machine learning part. It's important to also think above and beyond and know what to do with it, right? So now we're creating a website with some UI and UX designers. This is a total, placeholder text, don't read it. But essentially the premise being, what would it look like if it happened in your own backyard? So the idea is that we're trying to bring extreme climate events like floods and wildfire and smog closer to people. So to say, well, okay, well, Siberia is far and yeah, it's sad that it's burning, but what if it happened in your own hometown? What if that flood in Bangladesh was actually in Montreal? What if that the smog in New Delhi was actually in Toronto? So the idea is really to have an experience that will help people learn about climate change and also take action. So of course, action is kind of the center of it. And we're working with climate communication specialists, we're working with psychologists in order to kind of frame things in the best way so people are inspired to take action. So yeah, we've got our 3 events and people are going to be able to enter an address and see the visualization and see the different kinds of different events. And after that, click on Act Now and kind of learn about the action that you can take. So in a nutshell, things I've learned, I think this has been really a learning opportunity for me in the last 2 years. So what I learned about machine learning is that it takes trial and error. So in the coming couple of days and in the rest of your career, hopefully, learn from your errors and take them kind of as they go. And machine learning is not an exact science. There's parts of it that are exact science, but applied machine learning is a lot of trial and error. And often in applied machine learning, once again, the most elegant solution does not work as planned, and end-to-end solutions are not as robust as you'd hope they would be. And engineering solutions like pipelines can be robust and more flexible. So having several components, using pre-trained neural networks, using existing models, don't try to reinvent the wheel. If someone already has like a great segmentation model, use it, fine tune it. A lot of it is actually engineering and kind of Lego building. And also, if ever you do pursue a career in the field, you have to kind of be ready for the fact that sometimes the most impactful results, the ones that really make like a climate impact, are not going to be the most publishable in machine learning. So now there's starting to be venues where applied machine learning and applied AI with regards to climate change are being kind of lifted up. But oftentimes you kind of extract the machine learning bit and you publish about it, and then this is not the rest of the project doesn't necessarily fit in. So currently we're, for example, trying to publish our own results, and we're having trouble framing it because we're doing a task that doesn't have a baseline. We're doing a task that doesn't have a state of the art. No one really cares about it, so we can't like publish a data set and be like, hey, try to project flooding. People won't, right? And so it's really hard to frame it in a way that people at NeurIPS or CVPR or whatever are going to be like, oh, hey, yeah, this is a great machine learning paper. So I mean, of course, the end goal is definitely not publishing, but it is part of the academic life, I guess. So but be ready of taking a part of your research and publishing it in a way that works, and hopefully our community will move forward to more multidisciplinary and more kind of broad scoped research in the field soon. And as David said, as Priya said, machine learning is only ever part of the solution. And from the beginning to the end, other things must be integrated. And also what I've learned, kind of above and beyond machine learning, is that AI projects and machine learning projects are rarely a one-shot deal. Like you think it's going to be done in 6 months, it's not. If you really want something that's meaningful, that works, that's going to create impact, it takes time, it takes iteration, it takes learning, and it takes maintenance as well. Like you're not just going to throw your neural network out into the wild and it's just going to trot off. No, you need to own it and you need to maintain it. And domain knowledge is key. I think that had we been more forward thinking, more proactive about, for example, learning about climate science 2 years ago, we would have realized that this is not something that could be done easily or not in the way that we had initially thought, right? And this would be something that we should integrate upfront in a project and not, a year in. As I said, commit in time and effort. So even if you do, for example, an AI project in a hackathon or as part of like whatever your weekend project, your weekend and evening project, committing time and effort to maintaining them is really important. Even if it's just checking in, even if it's just like, oh, hey, is my thing still there? Are people using it? The number of GitHub repos that I found that people don't maintain just because, they've moved on to other things. And in the meantime, people are trying to use this code and, opening issues and having trouble and whatnot. I think that it's really important as a community for us to help each other and to, even if you made some crappy code that you think isn't going to help anyone, maybe it is, maybe, someone needed that exact thing. And so committing time and effort to maintaining code is really important. And I think that as well, learning about this field and being immersed in this field in the last 2 years, I have seen a lot of hype and a lot of kind of, we're going to save the world, we're going to stop climate change in its tracks kind of discourse, which, to be fair, I understand, and it could be seen as optimism, but it could also be seen as overselling, right? And so I think it's really important to be upfront about what you're doing, and even if you're doing something that's potentially world changing, but maybe it's only changing part of the world, not the whole thing. So, just being clear about, I'm saving the world by doing this, or by detecting this, by analyzing this. I think it's really important because, once again, this is a fairly new field. We're all in it together, and we're all kind of a piece of the puzzle. So if we're all coherent about what we're doing, it's going to be easier to build a field that incrementally grows, because science is all about, and I mean, a lot of parts of, I guess, society is incremental growth, right? We want to help each other move forward, grow together. And so being straightforward about what we're working on and how it can help is really, really important. So I hope that this is some somewhat inspiring talk, and that you will power through this weekend. And I'm really, really excited to see the results of your hacks and connect in the future if I could be of any help. So thanks.
Really inspiring, Sasha. Thank you so much for that. Do we have any questions?
No, we seem to be doing okay. No questions yet. Thank you.
All right. Well, you covered everything, I guess, Sasha. So
I guess people are tired too.
Really, really awesome to have you. And yeah, we're excited because now is the official launch of the hackathon. Everyone's really going to get started. We're doing team formation right after this, and we'll be doing it into the late at night and tomorrow, because people from all over the world. So thanks again to all of our keynote speakers. Thank you, Sasha. Thank you, Priya. Thank you, David. Thank you, LA. And let's bring back Monika.
Good luck, everyone.
Yeah, we can't wait until we see the results on Sunday, and we're going to be posting all of those videos for everyone to see. So that's exciting.
Yeah, thank you, Sasha. That was so great and such an inspiring story. I love the fact how you shared your journey and where you came from, and that like shift of career, and that inspiration. I think many that are listening and participating this weekend will use your story as an inspiration.
Yeah, absolutely.
Thanks.
And it was great to hear that, it's never too late to switch your career path to make an impact. Cool. So Monika, let's talk about what else we have going on tonight.
Yes, actually, we are ahead on schedule, but we covered a lot of ground in the amount of time that we kept you guys today with us. So what it means is now the floor will be to you guys, because now it's your turn to shine, to connect, to collaborate, and use all the amazing tips and tricks and learning that all of the amazing speakers today have presented, the data challenges as well that we heard from earlier this afternoon, but also some great insights from earlier this week. So I hope all of you are really excited because it's starting so soon and even sooner than we had planned. So maybe let's do a quick wrap up of how can people find the information. Let's say you're in a different time zone, you weren't able to watch today. So this video will be available on the AI Launch Lab YouTube page, and you had the information sent to you. So if you want to rewatch it, definitely feel free. It will be available shortly, right, Tim?
Yeah, absolutely. So Monday and Tuesday were a bit of carnage. Those days of live streaming didn't go well, and then even when they did go up, they actually got flagged by YouTube and taken down for a couple of days. We're going to try to chop them up and put them back up, but the live streams I think are up there, so you can see them in all of their horrific glory if you do wish to do so. Today's fortunately went really well, really smooth, no issues there. So thank you so much to the team behind that really stepped up in the last minute to try to pull this together. We wanted to do something stable, even though it had a little bit less of the frills, but at least it would work and there wouldn't be any issues with audio dropping out or stuttering or whatever. So yeah, it will be available, to the best of my knowledge, probably within a couple of hours for everyone to rewatch or to watch for the first time if you weren't able to see it live.
Yes, that's great. So hopefully you got to learn a lot, even though you're all sitting in at home. We know it's a pandemic, so hopefully you're starting the year on the right foot. We think that by working on this hackathon and having these great challenges that are meaningful and getting amazing insights from experts and like really amazing people that we've heard from tonight is really an honor, and all of you, I think, will have an amazing experience this weekend. So also I want to point out that already we've been seeing like quite some activity on the Miro board and on Slack. We see the busy bees moving around. So let's do a quick overview of what to expect tonight, but also Saturday and Sunday, since we might not have the opportunity for Tim and I to directly speak to you on a live stream until later this weekend. So let's put you guys all on the same page. So for tonight, what's going to happen is as soon as we finish up on the wrap up, we'll be opening the doors. Officially, all of you will be joining in the team formation process. So I'll give more explanations on how that will work and a bit on the process. But also tomorrow, what's happening is as of the morning, there'll be a few key ice freezer activities that will bring forward to you guys in order for you to check in with us, but also have a break. And then on Sunday is when officially we have the last day, you have your wrap up, and the submission of your projects will be at 6 p.m. Eastern time on Sunday, the 24th of January. But even after you submit your project through DevPost, there will be an opportunity for you guys to watch a live stream where we'll have a bit more comments and elements to close off the evening. So once again, I think you guys got used to a little bit more the process. If you have any questions, you can ask them either on the Slack channels. So there's a few in there that you could use to communicate with our team. And the great part about this hackathon is that you'll have facilitators and organizing team members 24/7 with you through the whole weekend. So we shifted out our team to make sure that there's always going to be someone from our team with you guys to answer your questions and to guide you. So we're really lucky to have those people with us. And thank you again to all the facilitators and the organizing team of AI Launch Lab and MTL Green for providing this amazing support through the weekend.
Yeah, awesome. So now we're going to, oh wait, should we discuss anything else, like, in terms of what's happening next in Saturday and Sunday, judging criteria, anything else that we need to go through?
Yeah, so keep in mind that for judging criteria, and we can definitely put some announcements throughout the weekend. In judging criteria, pay attention to that. Definitely what the flow of what would make sense, you guys as a team, is that tonight you're exploring which challenge you want to pick and which team members you'll be choosing to work with them. So tonight and tomorrow morning, we strongly recommend all of you to go with that process. As soon as you'll pick a team, throughout the day on Saturday, that's when you'll have a lot of our 30 different mentors that will be available at different times of the day to come and support you. So the facilitators will be visiting your team zones and your team space and coordinating to make sure the mentors can find you in the Miro board and meet with you. So be rest assured, Saturday, a lot of mentors are coming in. That's when they will be available. So pay attention in the Miro board on their schedule, and you can already have an idea which type of mentor and when you'd like to meet with them. On Sunday, that's where you guys have to start thinking of creating your submission, right? So as Tim and I explained briefly on Monday and Tuesday, is you have to allow some time to perfect your pitch, making sure that your idea expressing your solution is comprehensible within the 3-minute submission time frame. So we will be posting the format more clearly, but allow some time for this. And our team will be available to allow you to pitch, get some feedback on your pitches. So really don't underestimate that preparation time.
Yeah, absolutely. And some of the mentors that will be with us tomorrow are pitch experts. So definitely make use of that if you can, if you wish.
Absolutely. So really use the resources as much as you can. That's why all of us are here for. We're here for you guys. We're here to, watch you grow, to watch you learn, and really do not hesitate. You can recognize mentors and organizing committees and facilitators with their names. So both on Slack, you and the Miro tool, you will notice the last name of people that are on the organizing committee will have either mentor, facilitator, or organizing member attached to their name. So pay attention to that too, so you can recognize a bit who are the folks that could help you. Also, our team will be checking in with you as well through the weekend to make sure that you're not Saturday an hour before the deadline and you might not have still yet prepared your pitch. So we'll be checking in with you. There'll be a few checkpoints through the day tomorrow, but also Sunday. So pay attention to the announcement board, both on Miro and on Slack, to find out more on where should you be in terms of the process.
Yeah, and just to reiterate, we would obviously want as many people as possible to get into a team as soon as possible. But of course, some people are not going to be watching this live, or for whatever reason, they won't be able to find a team. So into tomorrow, our time, or maybe it's already tomorrow where you are, we will be checking in with you and trying to help you get onto a team if you weren't able to, and don't be shy. And if you are shy, we'll find you. So don't feel like you're alone in this process again. And I just want to inspire everyone that, of course, this is just the weekend, but this is just the first step. The reason why it's AI Launch Lab is it's the launch. This is the launch of this event, but it's also the launch of what we hope will be projects that will be taken forward beyond this event. And so we're going to do everything possible to support you if something is promising, and if there's a willingness to kind of continue on and a commitment, we'll do everything we can and put resources towards it, because we're not interested in just having demos that end up doing nothing, right? We want to take them to fruition and actually have them implemented. So that's the real end goal, and that's why everyone should race against time to try to achieve the impossible over the next couple of days.
Absolutely. And I think from multiple speakers today, you've heard and understood that there is a sense of urgency to tackle those key and critical elements related to the climate crisis and climate change. So your help will be needed not just for 3 days, but right away, right now, and for the future coming forward towards all of us at high speed. So to Tim's point, it won't be the last time we'll talk, no matter your experience this weekend. It doesn't mean it ends there. The network of AI Launch Lab, MTL Green, we will maintain, your engagement and the opportunities for you all to connect even beyond the hackathon. And we'll tell you more about it as we get closer to that.
Yeah, and even in the shorter term beyond the impact is that the prizes, we won't get into all the details of the prizes right now, but they include kind of fast track to acceleration programs, definitely our AI R&D mentorship programs, but also other programs as well that can help you maybe turn this idea into a startup, and time with some of these VIPs of some of the ones that you might have seen just earlier, and some others that might be speaking on Sunday, as well as in the future. Some of these people, even their friends can't get an appointment with them, without a month notice or a few months notice. So to be able to have time with them is really, really valuable. And I do want to announce that on Sunday, we will have Sylvain Carl of Second Muse and Real Ventures. He'll be keynote speaking at the closing of the event, as well as Nicole. I don't have her last name with me right now, but we'll announce it. Later from Academy of Sustainable Innovation. So those are going to be the two closing talks, and the rest of the closing will be kind of a celebration of your work. So we're going to basically show videos and maybe try to bring you up to kind of speak about your experience. So that's going to be exciting on Sunday. And I keep rambling on, Monika. I'm sure that we don't have much time before we go to the next steps here.
Oh, no, it's okay. I think it's important to mention, and we're so excited. Even for myself, for Tim, it was such a great experience. Like, it's crazy how doing a virtual event, you got to make friends with people that are on the other side of the continent, and without even meeting face to face. And truly, by onboarding onto this organizing team, we've made new connections, new friends, new synergies, and we're confident that you guys will feel the same way in this intense 3-day weekend with the tools to make sure to connect and meet those people through the weekend. So yes, so without keeping you guys longer, you must be fed up of listening and eager to produce and bring everything to action. So
actually, there was one more thing that Theo was telling us to mention, which is the checkpoints. So what can we say about the checkpoints, Monika? I'm not that familiar with the checkpoints, but I know a little bit about them.
Yes, no, exactly. I made the allusion to the checkpoints a bit earlier in my rambling too, where there will be moments where the teams there will be a check-in process with your teams. So we'll be able to check in with you to make sure you are first in the right step throughout the process, throughout the weekend, so that you follow certain steps, but also to give you guys feedback on how is your team performing, where you guys at, how can we help you. So the facilitators and organizing team will be there to assist you, and do not hesitate to use them. They are there for you, and we all are. So now it's your time to shine, maximize your learning experience, because Time is ticking and the planet is not going to wait after us. So go crazy, make the most out of it. And I promise you, you will learn no matter what this weekend. And remember to have fun as well. All right, so I guess we're ready for team formation, right, Tim? Let's give a few pointers on how this will work. And that's where all of you will be able to now shift forward the evening, and we'll be able to close the live streams shortly. So there are 4 steps to form your team. And please pay attention to the announcement board on Miro and also the announcement channel in Slack. So as of in a few minutes, we invite all of you to join the Rally link. Rally is essentially a video chatting platform where you will be able to finally meet the participants and choosing who you'll be working on this weekend. In the Rally tool, there'll be team members, facilitators to guide you. Essentially, there are 4 boards. So 4 boards is for the different challenge types. 1 represents the Kaggle style. So for Kaggle, essentially, there are 3 challenges there. So we have the sea ice challenge, wind energy, and super resolution. So if you are interested in meeting people that want to work on those, you enter that room. If you want to work on DataViz, there will be 2 projects in the DataViz room, which is reducing CO2 and smart building. So same thing, if you want to meet people there, you'll go in there. And the 3rd board will be projected impact. So we'll have Be Healthy and Sewage Overflow. So if you want to work on those, you'll go in there. And the 4th board will be the Open Challenge Remote Communities from the indigenous group that we heard of today, as well as the AI Artist Challenge. So those are grouped under 1 board. And if you need help at any moment, there's a 5th board called the Help Desk, where you'll have someone from our team. If you find Paul there, don't hesitate to bug him. He'll make sure to direct you in the right spot. But within each of those, you can change boards at any time you want. So you're free to move from 1 board to another. And I call them board, but see them as different rooms. And within those rooms, there's different tables. So imagine you are in a restaurant, you can switch different tables, have conversations with different people. So you'll learn the tool very quickly. You just have to kind of switch rooms and you'll see there'll be people there helping you around. So this Rally link will be opened all night, okay, up till tomorrow. So you guys can join in that link anytime when you realize that you have to form your team, even for those listening from the other side of the globe. The Rally link will be available all day. Once you do choose a team, there's 2 steps to follow following that. You will have to create a team profile in DevPost. So the link is posted in the announcement. You'll create your team over there. And also you will need to fill an official registration of your team through a Google form. And in there, you will really specify what is your team name. From there, this is where you can go in Miro. And in Miro, then you have to claim a team space. So you can claim the team space that you will, but please use the same team name that you used for the Google form. So your team name, this is what we will use as a reference to find you. And make sure you choose 1 team space for the challenge board that you chose. So remember, there's 9 challenges. You can find a board for each of the 9. And within that board, you can claim 1 square team space and make it, personalize it to your liking. But you have 1 team space per board, depending on the challenge you choose. So those are essentially the steps. And we encourage you to work on this tonight. Tomorrow morning, we will be checking in with you, and we suggest to aim before noon Eastern time to form your team tomorrow, Saturday, January 23rd. So try to form your team by that date. But if you cannot, for whatever reason, you didn't have a chance to log in, do not worry. We'll make sure you find a team and we can reshuffle you teams. That's why there's always going to be someone in that rally link talking to you, forming you, and use also the Slack channel Team Up if you want to introduce yourself and find some people there as well. So hopefully you guys are excited. All those instructions were posted on both collaboration tools. And like I said, feel free to reach out to facilitators. They have in the main stage also a space where you can contact them. They will reach out to you as well. So do not hesitate. We'll be all over the place online to help you out.
Awesome. And Theo is reminding me that the as part of the checkpoints, there's this team-to-team feedback, which we really would encourage. As we had mentioned, and I think I don't remember which speaker had mentioned, it's about collaborating, and we can do this together. Of course, we understand we can't do everything just this weekend or with AI, but yeah, we really want to stress collaboration. And so those team-to-team feedback sessions, we think will be really valuable. And you will get bonus collaboration points for doing them.
Exactly. And that's a good point. Use the Miro board, because the artifacts you put into your team space, how are you helping other teams, will be taken into account in your final judging criteria. So it's really a value we want to bring forward, because truthfully, the only way we can approach climate change is by working together and not in silos. So guys, we have faith in you and we're super excited. And yeah, I guess we're almost 8, so I think we can make sure everyone goes on that link. Ming will be posting the link also on the live YouTube feed. So if some of you want to have a quick reference there, otherwise it's posted on Slack, the channel Team Up, but also under announcement. And in the Miro board, you'll find it as well under announcement. So I guess we'll see you there. And to end the day, I'm Monika Potocki, once again, your co-host with the handsome Tim here with me today and all week, co-founder of MTL Green.
And co-founder of AI Launch Lab. And thank you so much for joining us today. And thank you for joining us if you're watching this later. And we look forward to seeing what can be accomplished this weekend. See you soon at the brainstorming, team formation, whatever it is. See you soon.
Yeah. All right. Time to network and find who can, you can attract to your team space.
Cool. So are we going to be streaming that now?
I don't think we need to stream it if everyone joins there. So probably we can close the stream and make sure everyone gets on there to start forming their teams.
All right, sounds good. That also lets this get uploaded sooner for everyone else.
All right. We'll see you guys on Rally and speak to you soon. Have fun.
Yeah, have fun.